Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook. I'm joined with Greg Volk and Dennis Allen. Greg is on the one with camera, and Greg and I are Denny and I are calling in. There's something very important to share, some new research, and actually follows from two papers that we have written. Actually, kind of, you can parse it together from these two papers. It's really extraordinary. I got Greg here to, when I start, overselling it, that it's more wonderful than it really seems. He's going to slow me down, bring me down to earth, and I think this is important.
Sounds good.
But I will tell you, for me, it to me is something. To me, the greatest mathematics finding since Euler found exponentiation. So wow. It really does something amazing, and it's a tool that all mathematicians can use. But I can't really show it. If I just show it right off the bat, it's going to underwhelm you. So Greg has to kind of say, no, it's not that big a deal, because it's not. It's really simple, and you all should have figured this out. But I will tell you, it's a very useful tool for physics, science, and if you have your own science model, it has applications all over the place. And I'm going to introduce it through the two proofs that we are going to discuss here. A direct proof of the Riemann hypothesis, which Greg and Denny are co-authors on. Mm-hmm. And if you're new to this, I understand your skepticism, but we're going to go over it. It is very simple. It's been out for 5 years. There has been errors and typos in the beginning, but
nothing of substance has changed in 5 years.
Nothing of substance has changed.
And it's had 20,000 reads.
Yes, which is significant. I mean, if you're Taylor Swift, you may be underwhelmed with that, but I'll tell you, for math papers, that's actually a lot. So please stick by as we get into this. This is really, if you're a mathematician, I guarantee you're going to like this. Now, you may be interested in one component of it that I'm not interested in. For example, Denny is really very fascinated with the concept of a proof that follows from this of the Euler-Mascheroni constant being transcendental. I'm not as impressed with that because it became very easy. So obviously the problems that I work on for a long time are difficult. But that is one other proof that follows from this. I'm telling you, it makes solving math problems, typical math problems that have been hard, very easy. And I think the reason is, I can explain the reason why. It's this tool makes a large number of math problems very simple. So we're also going to go through the proof of the direct proof of the Birch and Swinnerton-Dyre Conjecture, which we also have. And I'm going to show what's really interesting is the way those two combine. When I first brought this up to Greg with this version, was 6 or 7 years ago, before we actually uploaded the first version of the paper, I said, I think I also could prove the direct proof of, the Birch and Swinnerton-Dyer conjecture. It took a few more years later, but you'll see why they're related. It's related with this new finding. It's very, very interesting. All right, so let me get to it really quick. But
Can I just say something real quick? That is,
do.
I think what we're going to be talking about is taming infinity. We talk about renormalization in physics. We talk about extension in mathematics, in a Riemannian sense. It's a generalization of all of that stuff, and yet it's so simple. Is that fair?
Yeah, purely through arithmetic. Yes, it's something. So even quantum physics is normalized, with this. We'll go over it. But it's more
I would say also most of the problems in math today are related to taming infinity. Fair enough?
Yeah, exactly. And
because that's what this is
problems
about.
Because this tool hasn't been around, and so it's been difficult to understand that concept. With this tool, those concepts are very easy to get around.
And that's why you're making the big claims you're making. And we'll see if they're true.
Yes, it's not little. And if you what you can do is I made a few papers. I'll give it at the end. A few papers available. Just copy them, paste it into ChatGPT, and they're gonna or Grok or whatever, and they'll walk you through it, because a lot of this is it's hard to think in this new way. All right, and you'll see why. But first, let's speak about the Riemann hypothesis, because I'm gonna introduce this other concept slowly. Okay, so if you go, I'm really fascinated with Brave, the search engine. Some people say it's too woke for them. I haven't seen that to be the case from my end, but I guess it depends what you're researching. But if you go in there and type in a direct proof of the Riemann hypothesis, it should be the second one that comes up, first or second, and then you can kind of link to it. But you can actually ask, Brave has AI built into it, so you can ask some questions. The big question, and this was always your concern, Greg, was are these changes we're making over these years, these updates, changing the core of the paper. And Brave references, look, are you able to see my cursor, Greg?
Yes.
Okay, so
but I can't read the text. It's too small, but that's all right.
That's okay. But down at the bottom, it references different papers, the AI, and it goes through and says, no, here are the changes. So I asked, like, has the paper changed in the various versions much from 2020 to today? And it says, no, the core argument and structure of the paper by Cook, Volk, and Allen have remained consistent, and go on and so forth. The point is this, is even if people are not acknowledging and defending the proof, that's okay. Because as we all know, AI will be calling the shots, so to speak, in many ways, and they are currently keeping a history of these results. The AI loves it. And AI, I just kind of went through a really interesting thing yesterday, actually took a whole day, between Grok and ChatGPT. I had them debating on opposite sides of the paper. I said, you be the angry, bitter referee of the journal, and you be the good, normal mathematician defender. Both of them want to be the good one. It turns out Grok finally volunteered to be the bad cop, and Chat ended up being actually a bad cop in disguise, because I had to like defend the proof from both ends. And after a while, I'm like, wait a minute. And then eventually Grok gave in and said, okay, this is right. But every new version that comes out with these, I do run it through to check to see if there's something new they find. And a couple new typos. The paper has been updated yesterday with a couple typos. We called it a partial sum at one point, and it was actually showed an infinite sum, things like that, which matters. They matter, even though I did say in the text that we're going to get to the point. Okay, so where to find the paper? Again, it's at ResearchGate. And yeah, I think last I looked, just over 20,000. So I figure it's good to do this update, especially in light of what's going on.
And that's been fairly steady. It's not like there's been a lot of reads all at once. It's just been a steady, slow, steady climb for the last 5 years, roughly 4,000 a year. Is that fair?
Yeah, you could look back. We're kind of doing about a video a year, and you'll see it. I don't know where it was last time.
But
I think it's a little bit more
pretty regular
than last year.
Yeah.
Yeah, a little bit more lately, because that short that I put up is taken off. I'll show you where that is. I have it here. If you want to hear the Riemann hypothesis short in just under 3 minutes, I put up a short over YouTube. It's kind of get out. But basically, this paper, to say it is not a little thing, it is in the top 99% of all papers uploaded in 2020, even amidst COVID and all the science papers there. To this site, but this site has thousands of well-established mathematicians. I mean, Pierre Delaine. There's many great mathematicians on here, and so it's. I mean, and the research is deep. They have stuff on sociology. I mean, so it's really so. The research score, while 20,000 reads is not a lot, that's still higher than 98% of everything ever uploaded to ResearchGate. So it is significant. It is not a small paper. And you'll see why. It's a very, very straightforward, simple proof. Okay, so the direct proof of the Birch and Swinnerton-Dyer conjecture was uploaded a couple years after that. Not as much excitement. We're getting about 1,800 reads. Okay,
it's not as big a deal as Riemann.
I don't think so. You know, there's been movies that talk about the Riemann hypothesis, and it's a lot more. So
it's on the millennial.
What's
Birch
that?
and Swinnerton-Dyer. Birch and Swinnerton-Dyer is one of the millennial prizes, but it's not as big a deal as Riemann.
I think it probably is a big deal. I just don't think in people's eyes. I mean, it has some far-reaching results, but a lot of people don't understand it. There's a lot of the equations are very complicated to calculate, so there's some differences in that way. But with these new findings, Greg, those difficult calculations are now made easy. So I will kind of show that too. Yeah, so calculating the zeros at the L function of elliptic curve at s equals 1 is now can be done with an infinite series. So that follows from it too.
Can I just jump in that L functions are one example of infinite things, things that behave like infinity, but you have to renormalize them or whatever. So L functions are well known among mathematics.
Yeah, they're like the analytic continuations of L series, which are, they have a functional equation. So we'll get into that. But like I said, if you really want a quick summary of the direct proof of the Riemann hypothesis, check out this short here. Go to my site. You're at my site already. Just click on shorts, and it's there. It's probably got about closer to 12,000 views right now. Let's take a couple days. But I'll tell you this. Oh, and if you want to check out this proof of the resolution of the Russell paradox, that's pretty cool too. In any case, we got to zip because there's many things to get through.
Okay.
All right. We got to go through the entire Riemann hypothesis, and we got to go through the entire Birch and Swinnerton-Dyer conjecture. And at the very end, we're going to give that. I'll explain what is going on with both these proofs. Were done using these methods without us knowing it. And when you unify them together, I'm telling you, your mind's going to be blown. It's super cool. And the best part about it, here's the best part. What we're going to show can be reduced to standard arithmetic, so you never even need to acknowledge my work. You can steal it, and I don't care. Just use it because it's a very powerful tool. So you can actually kind of do it all. You don't need to reference our work. Just kind of go do it. I'm telling you, use this tool. It's really fascinating. When I get to it, we'll show it. Okay. All right. So the Riemann hypothesis, like I was saying before we came on, it's so simple that it's almost frustrating of why people can't get it. Now, the only thing that gets complicated is there's 3 steps. Well, they get it. They're silent. So that's the issue that concerns me, because AI is not silent. And I wonder if AI does take over, how it'll feel about a bunch of mathematicians staying silent.
The world's going to be a different place 10 years from now
they're
than it
going
is
to weed
today.
out. I know this is important. People need to start stepping up for the sake of competing with AI, because AI is already all over it. And we do not want mathematicians to become, well, fish food, right? Okay, so we have to stay active and start going, okay, fact, move on. Fact, we have to stay as active as AI or better. It's certainly not as creative as we are yet, but it certainly has access to all sorts of theorems and in the literature at our own access. And I'm telling you, it is solved. It's trying to solve proofs on its own. It's going to make people obsolete if we don't get our act together. Well, I am trying hard, and I think this new tool is going to help y'all. The Riemann hypothesis is in 3 steps. I don't care if it is the Riemann hypothesis or proving the square root of 2 is irrational. It is simple. If you understand a little calculus, you can get through the first proof. If you understand a little bit of limited analysis, you can get through step 2. At that point, it's just algebra. All right. So the final result relies only on algebra. Obviously, you have to do these steps. That's a little bit more, but we're gonna get to it. Okay. So we're gonna prove step 1. This is a funny looking equation, Greg. What do we call that?
It's just a second order differential equation.
Yes. So you went to college for this. Can you explain to the readers, the lay mathematicians, what this is?
Well, the derivative with respect to t is just like a frequency, and omega is just like a frequency. So we have frequency squared plus 2 times a frequency squared plus a frequency squared times a constant. Of course, it's clear. The epsilon, the coefficient of the middle term in if you're going to analyze a function, that would be like the resistance, because an oscillator would just have a second order term and a first order term and a 0th order term. So the first order term is sort of that's the drag, that's the resistance coefficient, kind of like. The other thing is you can also reverse it.
Like a swing eventually slows down. Like
you can invert this thing, and you can the role that epsilon plays. You could just multiply everything through by 1 over omega sub s and c sub s, and you could get epsilon and the zeta function to reverse their role. So it's like the zeta function is like the drag of epsilon, and epsilon is the drag of the zeta function. So it's just a way to interpret it. And I would just say you don't prove it, you state it. It's just, we're going to say that it has this form. That's how I would view it.
Good. So let's get a physics analogy for people. If C sub S means position, then what would the next the term to the left?
Well, position, velocity, and acceleration. So if you can think, second order differential equations are used all over the place. So the most common example would be a spring. So as the spring moves out, its position is the equilibrium in the middle, and then as it kind of just moves out, then it starts to slow down. The acceleration's pulling it backwards, and then it goes the other direction. So a harmonic oscillator. But eventually it stops, and that's the damping term in the middle. That's what causes it to stop. The bigger that term is, the faster it stops. Does that make sense?
Good. That's
In a simple
perfect.
harmonic
Yeah.
oscillator or a pendulum swinging is going to behave by an equation like this. And if there's, if there's no damping term, it's just going to go forever. But the damping term tells you how fast it's going to slow down. Does that make some sense in terms of
Yeah.
physics?
And the
That's what I
damping
see.
term. Yeah.
In
And the
electrical
damping term is
engineering, we see equations like this all the time. It just, that it'd be like a capacitor on one side, an inductor on the other side, and then the resistor in the middle. That's sort of like the damping term. We get the same kinds of equations all over the place with electrical engineering too.
perfect. Have you ever seen it with being equal to the zeta function?
Well, not until you.
No. Yeah. All right. Just teasing you. Okay. So yes, what this does is it's saying that the Riemann zeta function can be expressed as a harmonic oscillator, driven, damped, depending on how you want to approach it. All right, now let's skip, and that t equals 0 means like an oscillator happens over time. We're saying at its initial starting point. Is that what that means? T equals 0?
Yes, that's what it means. So we're
Equals
looking at a
0.
particular
Everything
point in
reduces.
time, and we're saying what is the change at that point in time of c sub s, and that would be like a velocity and an acceleration term at that point in time. That's
All right.
normal thing to do.
Yeah.
The only thing, again, in a engineering equation, you might want to know, well, what's the the velocity and what's the at t equals 0 also. That'd be the only thing that a mathematician might want to know. But
We will give that.
We'll skip that for now.
No,
Yeah.
no, we have to define that. We'll get to that because we have to define what c sub s is, and that would give the velocity and all of those.
Right, and those would be called the initial conditions for whatever that's worth.
Yeah, there you go. Perfect. That's the I was waiting for the initial conditions. All right, now let's skip. We got to prove that. Then let's skip to the next one. All right, so this is explain. I was going to have Denny explain this, but that's okay. I'm going to do it quickly here for him. So if you look this is. You think of this as a radius, right? So if you have this spiral, let's find it. I probably ought to wait for this. We have this spiral, and the spiral is in the lower. Do you see my cursor?
Yeah. Can I just throw that S is sort of like the opposite of T. Where T is time, S would be like frequency.
Oh, for the last one. Yeah, I know, but we got to move on.
But we're talking about S now in the second equation.
Yeah. S is very, very important. All right, so let's get to this spiral. So all I'm going to say is this minus 1 to the power of n times n to the power of minus s creates this counterclockwise spiral on the complex plane that always goes to 0. And if you take that sum, you get the minus Dirichlet eta function. All right, and this term in the first to the left in the numerator and the left is constant with respect to n, of course, it's constant for s, and it's identical to the bottom. So basically, you have k minus some function, the absolute value over k minus some other function. This, if both terms, the second terms of the numerator and denominator, both go to 0, and they do because we're going to consider only the zeros of the eta function, and the bottom always goes to 0. What are we left with? K over k. What does that give you?
1.
One would think, right? But interestingly enough, as this is decaying, as we're trying to limit, when both go to 0, we don't end up with 0 over 0 because this first term goes to 0 when the real part's 1/2. What happens is these two ratios decay at different times, and exactly the speed difference is 1/2. Now, this ratio of radii is going to become very important when we talk about mixed rates, because this is almost always going to be the tool we use to do it. The mixed rates is going to give to the new big thing. All right, the last part is the Riemann hypothesis, as stated, that all the zeros of the Riemann zeta function within the critical strip are.
And by the way, step 2 is the more.
Oh, hold on. And then is equal has all right. When you interrupt, I got to say it over again.
I'm sorry.
The Riemann hypothesis, for those that don't know, is that all of the zeros of the zeta function, zeta of s equals 0, when the real part of s is greater than 0, that's this region called the critical strip, they all have a real part equal 1/2. That's what the Riemann hypothesis is. We also have to prove that. Yes, go back to your thing. You're saying.
Well, I was just going to say step 2 is by far the most difficult part to prove, but it is pretty straightforward. It just takes a few steps. That's all.
Yeah, if there's anything that's going to take, like, is there something hiding around there? It's always in this one, and you can
Yeah.
get through it. The first step has been acknowledged by many mathematicians at universities. The first step, our proof is solid. This one they've gone quiet on. The reason is because immediately when you get this result, you get the step 3 within one sentence.
Yeah.
So they really should be kind of lumped together, which is kind of why I put those little braces there. But let's go, because it's going to be fast. Let's go to the proving the first. We'll show how it does. All right, this is how we do it. So the first big mistake all of you skeptic mathematicians are making is saying, oh, but I can take this Euler product that has zeros on the critical line and off the critical line and so on and so forth, and I'm just going to step in and say, you're doing it wrong. All right, so there's something called Selberg Euler products, or something that you can multiply things in to create your own function that looks like an Euler product that has zeros on the critical line and zeros off the critical line. The key issue is they cannot be defined in terms of infinite series, nor integrals, or at least they never have been. The key point to making that argument is somebody produces a purported proof, and this is what I hear from the editors. It's like 99% of all papers claiming to prove the Riemann hypothesis begin with the functional equation. And the moment editors get it, they immediately throw it aside, because anything with the functional equation, they've become so, they're tired of seeing it, because they almost all of them can be disproven with these products that I'm talking about. We begin with an infinite series. All right, we begin with a Dirichlet series, and where it has the form of a of some variable times n to the power of minus x. Anything in that form is a Dirichlet series. The zeta function is the stereotypical one, where a of some variable is simply 1. So it's simply n to the power of minus x. So we are beginning with an infinite series representation of 3 variables. Here they are. Oh, sorry, not infinite series. No. The function, the summand function is here. It's a little long. Don't worry. It gets us where we want to be. All right. And then by applying it to the infinite series, you see how we get it. That is our function we begin with. We define this, and we're defining it as alpha. And alpha, yeah. The sum is alpha. Function inside is a. All right. Little small detail, a and alpha. All right. Alpha is what we're interested in. We're going to call that the decay constant. The decay constant divided by frequency, the fundamental frequency of a harmonic oscillator, is this term Greg was talking about in the middle. The damping, what is sometimes called the damping ratio, or damping or resistance of the oscillator. So the decay constant alpha over the frequency gives that. We're going to get into that. So we need to define that. And it seems like I skipped this slide. No. All right. Now, here's what's interesting. We can take this and we can apply the Abel-Plana formula. I don't show it here. Got to get through it. All right. Abel-Plana formula. It applies very nicely and neat. All terms are defined, and it converges for any complex argument S, with the single exception S equals 1. Quick little thing to note, though, we're going to now that we've done this analytical calculation, we're going to truncate certain regions, and we're going to do that with the complex conjugate. Now, then no longer is this function analytic, but it doesn't need to be. And so that was one of the first things Grok brought up. ChatGPT defended it, said no, it can't, and Grok conceded. Denny also brought this up in the early years and said, well, at this point, we're not using analysis. The proof doesn't depend on it from here on out, so it's okay, except for a couple areas. There's a couple things to note that, but we are ending up with complex conjugates. Now, we can't say that the Riemann zeta function has these in it. It's alpha. So if you think of a tow truck, how do you know if a tow truck's strong, Greg? Pickup truck. What's the best way to find out if it's strong?
Have it pull out a tree. I don't know what.
Tow something, right? It's a tow truck. It should tow something. Yeah. So you got to attach something to it. And so this is exactly what Helmut Haas did with the elliptic curve. He attached the zeta function to it. In a similar way, what we're going to do is we're going to attach this alpha to the zeta function through the harmonic oscillator. We have to attach this. What this gives us is an offset. Because look at when we get to it, we're going to show you. It is identical in structure with the zeta function, except it's offset. Remember how that applies to what we're coming to, Greg, right? This offset is what gives us the tool to do it. So there, I told you before, alpha over the fundamental frequency is equal to nu. So what we're going to do is we're going to get rid of, go back a little bit. We're getting rid of this Q, all right? And Q is analytic, allows it to be analytic. We're saying no, we're going to let Q only equal complex conjugate of S. Now that we're done doing that analysis. All right, here we go. Now
alpha went from 3 variables to summing over 1, reducing it to 2, and then assigning the third variable to the complex conjugate of the other. So now we're down to just 1 variable.
You got it. Now we're even going to reduce the frequency and say that it is defined by S as well. It is simply I times complex conjugate of S. What that's going to do is the complex conjugates are going to cancel when we arrive at the zeta function, because we can't have any zeta functions or complex conjugates in the zeta function because it wouldn't be analytic, and we know that it's analytic. So we have to can't cancel them out. Letting the fundamental frequency equal that does allow that. So which is what you were saying, how S is connected to T is frequency and T. So there is how that can take. So basically what we've done is we have attached the zeta function to this thing. We're going to see how strong it is and how it behaves. And here we go. So we have to define, like we brought up that C sub S, if position, then its derivative would be velocity, and the next would be acceleration. We have to give that a functional equation, and here it is. One that makes sense. It's not arbitrary, it's directed to give us the result in the form that we want for the zeta function in the end. And again, all of this has been confirmed by many mathematicians. It's not controversial at all, and it is novel, and it is useful. Everything for the proof follows from this. This is one
and that starts to look like an Abel plana there, that a little bit.
Yes, it does very much, because the first term is the first term in many forms of the zeta function. So the Abel plana formula, if you go to Wikipedia, many of the integral series has this 1 over S minus 1 there. And the reason is because that is the component that doesn't converge. That's the infinite, the pole at S equals 1. So obviously if S is 1, then you see how it explodes.
Yep. I hope you don't mind my interjections, but Abel plana has 3 terms also. And that was part of the reason why you came up with this quadratic formulation in the first place, like 10 years ago, right?
Kind of. I wanted to have a machine. I want to represent the zeta function as a machine first, and the Abel plana formula is way out to get to it.
Well, that's what I noticed 5-6 years ago, was that there's 3 terms, just like there is in the oscillator. And that's not a coincidence.
Because you run in. No, it's not. The Abel plana formula, when looking at it, is what you said. It was the research that made this possible. It said, I know how to make this now a driven harmonic oscillator. I know how to make it a machine. I wanted to have it operate as a machine, that behavior, so I could better understand it, but also that you can prove it and break it down to something that's standard, that's taught art in classrooms. No new physics, no new math, that kind of thing. So I wanted to tie it into something that already exists. The Abel plana formula, having the 3 different terms, definitely does it, because if you have 3 terms and only one term goes to 0, then you have only 2 options. That's what separates the zeros apart. Critical zeros and the non-critical zeros, if they should exist. Because if you look to this top, that second term is the only one that possibly could go to 0. All right, so it has upsilon. So the first and third term can't go to 0 because, well, one S could make it go to 0, but S isn't a 0 zeta function. So it's that second term is the issue. And so then all the other zeros that could cancel would be when the other 2 cancel the third. So yeah, A plus B plus C is only 2 possibilities, and it's a way of separating the 2 types of zeros. And that, yes, hasn't changed from the beginning. It is important. There's many ways you can reform like this, but this one makes it most straightforward. Okay, so that's what we get. And if you expand that out, given what we had upsilon, I said epsilon is defined as an integral. Yeah, I'm gonna say upsilon. The people are
epsilon's a different character.
I know, but and you don't say it that way. So I'm not Greek. I don't know how to say it. So here's.
Well, don't say epsilon.
By the way,
what talking about.
By the way, I'm not going to comment in the comments anymore. We can't, because I've looked into it and it lowers the algorithm. So sorry if you guys have a really good finding, I'll make a video about it, but I'm not going to comment in the comments anymore. Okay, I'll get into that later. So that if you expand everything and show it, well, you get this beautiful cancellation. It explodes first, but then it cancels to the Abel-Plano formula of the zeta function.
Mm-hmm.
Yeah, so that this last equality at the bottom, 1 over s, that is the Abel-Plano formula, a representation of the zeta function of what we were just talking about, having the 3 terms. So that's exactly what happens. Okay, it then proves it because we showed now that at t equals 0, and there's more steps a little bit in the paper, you can go check it out. All right, now we got to prove this, and this is where the meat and potatoes is. I mean, obviously, this makes so many things possible. There are different ways to prove it at this point, because you have a machine. You can look at it many different ways to find solutions to it. To me, this is the most interesting, and it has this really neat property that, well, let's get into it. We got to prove this, though, because it gives us the implication we want. So again, we were talking about that point. So let's consider a point. Let's consider it t, so it's continuous, okay? So it's not just integers or natural numbers, 0, 1, 2, 3, 4. It's going to be any point on the complex plane, and that we're going to call it z. All right, z sub t, s of t, and t is real.
So just to be clear, z often means integers. You don't mean that in this case. You mean anything, any complex number.
It's just
okay.
Yeah, it's just a
and
variable.
T can be any complex number, and S can be complex.
No. Real number. Good question. It's a real number. And this is the question: is what are we using? Principal branch? Are we with these exponents? Let's just say you choose. It doesn't matter.
Okay, so T is in the real. You did say that. S can be complex.
T is real. Yeah. So, but like if you think, so if minus 1 to the power of t, if it's real, then it opens up that it's being e to the power of minus, what is that, pi, something like that. And then you have multiple branches. That's fine. It doesn't matter, because what we're going to do is we're going to reduce it down. So for simplicity's sake, you can use it. Oh, and also if you use any other branches, they go outside the critical strip anyway. So it's not something we're concerned with. So just use the principal branch and consider this a spiral. Long story short, that is always going to go to 0. It's not hard to show. There's many proofs out there already that use this because of this. If we sum this, then we get the eta function, or in this case, the minus 3 eta function. Now, this function is really neat because the infinite series representation of the zeta function does not converge in the critical strip. So it does not converge between real part s, 0, and 1. But the Dirichlet eta function, I'm just calling it eta function, does. And the analytic continuation of both of them give this relationship where it's simply a multiplicative factor of the zeta function. See this? I'm hoping you see my cursor, right? So 1 minus 2 to the power. So anyone familiar with this knows this relationship. It's all over the place. It's well known and understood. All right, but we're interested in that point spiraling, okay, at this point. Now, just a little bit of talk. I think I just kind of said this. So we're going to study the relative rates of convergence. Now, I have this issue with Zoom is showing something that's blocking the last equation, but I can't really explain it very well, but I think it's the same one we just looked at. Oh, no, this is what. Yeah, I can't move that.
I mean, I can see you got a bunch of text here, and thankfully this text I can read. It's large enough.
Yeah, so there's some points I just had to fit them. All right, if we look at the bottom equation, we don't need to read all this. This is from the paper. We could do this with the Dirichlet eta function. We're taking the sum over the sum and function. That's all it is. The partial sum, I should say. So that's why it shouldn't say we shouldn't have this infinity. That's a typo. It should be make n equal k and then have up to n or whatever. But I kind of rewrote the paper anyway. But long story short, the partial sum of the eta function or the minus eta function over its sum and function. Absolutely. Does that make sense, Greg?
Yeah, I mean, you're doing a partial sum and then you're taking the number to infinity after you've done the partial sum. So it sounds like a semantic difference, but to a mathematician, it does matter.
Yeah, it does. This shouldn't be the infinity here, but it's okay. It's the partial sum is what we're interested in.
It's all about convergence and so on. But
yeah. All right, so what you find with this is that for all of the non-trivial zeros that we do know of, all the do all lie on the critical line have real part 1/2. Interestingly enough, this limit also equals 1/2, and but there's no way to prove this that I've seen from this alone. However, when you offset it, which is the theme of this video, when you offset it with alpha, then you get your proof. It goes around the problem. It's like a tow truck towing something. Now you have something else to see its behavior. And then the proof becomes very easy. It comes, and the alpha comes from the oscillator form.
Tow truck helps tow itself?
Well, I don't know. No, right. But you can understand it. You can understand it. But here's the understanding. The analogy is that you get an understanding of the tow truck by what its tow is. So right now it's towing this term over here.
Right.
So everything to the right is well, it's pretty much it's a multiplicative factor of the eta function. You see, so it's all there, and this is an eta function actually in there. So it's just 1/2 times s minus 1 squared times zeta function. That's all the second term is. So the only zero in there is the zeta function. So if that's 0, now we have something left behind. It's the second term. That's our offset, and that's constant with respect to s. So it's very interesting because if you look at this numerator, that only has zeros at real part 1/2. Question is, can we prove the Riemann hypothesis with this? And you can. So we're going to take the ratio. We're going to check by the behaviors. So again, we have, if you look at our function, this ratio, our ratio, easy to remember, and we're dealing with absolute values. We basically have some constant k minus some function that goes to 0. We only care about the zeros, over some function k minus something that always goes to 0. Can you restate that? Is that simple? K minus 0 over k minus 0. It's just how does it get to 0? That's all we're dealing with it. So we're going to call that offset amount s minus 1 squared, all that, the first term. We're just call that k for right now. And then I'm going to move my zoom controls. And that gives two solutions. Okay, there's one of them is extraneous, and it's very easy to see because it sends you outside of the critical strip. So we're not interested in that. We only care about what's in the critical strip, and so we're only going to use the first one, equality of k. And what we do is then when we solve that, so all right, it's the first one, s minus 1. Yes, the first solution here is the one we're going to use, and we're going to now set it equal to k, and we're going to show it in standard form, and then we're going to solve for z, that point, that spiraling point, right? This is very important. Now remember, if you have, interject. Go ahead.
Well, I was just going to say one way to think of you were talking about the offset, and is it fair, Jeff? I'm just trying to make this more clear for other people. Would it be fair to say that we have like a solution that we can't that's unmanageable, and another solution that's unmanageable, and then you take the difference and you're just left with the offset, and that's manageable? Something like that? Is that kind of what we're doing here?
Something like that. It's easier to describe. All right. So when I show the submission rules later, it's easier to show. For example, without referencing the work I've been working on.
I didn't mean to put you on the spot. There's another way. I've been through this a million times, but it's like a new way of looking at it.
You got to make it in a way that everyone understands it. Just think of it as like there's a problem area. We can't see it very clearly, and so we shift around that problem area. Now we can see. It's like putting a mirror around a corner. Like if you ever saw Saving Private Ryan, they put a mirror around the corner and see where the soldiers are. It's kind of like that. You're looking around the problem or the unknown. That's what these offsets do. And so it's a function of itself, and it actually ties into actual physics. A decay constant is a very real thing. So that's kind of what we're doing. It's just there's just not enough information about the tow truck until we put a tow on it. That's all. That offset is the load. So we have to add something to it. It can be a plus or minus. We're offsetting a +1 or plus some section. So that's the best way I could think of it, is we don't have any information about the tow truck. Does it even run? I don't know. Put a load on it and pull it. If you pull it, then I believe you. That's kind of what it's doing. It's the best analogy I can think of.
How about like an electrical circuit? You gotta turn it on or before you know what it can do. I don't know.
There you go. And then you got an expectation of what it's supposed to do. Something. All right. So then we're going to solve for z. It's just algebra at this point, right? But here's the tricky thing. We know that z is going to go to 0, but because we're dealing partial sums, we can't do this in the wrong step. Otherwise, you end up with a circular argument. You're saying that even though there is only 2 possible solutions for r over here, 1 and 1/2, there are only 2. You can look at it. If this goes to 0, the numerator goes, the second term goes to 0, and the numerator or the denominator second term goes to 0, you are left with k over k. That is going to be 1.
Right.
The only other possibility is whatever causes the left term to go to 0 also. And then you got a really neat thing. The left term only goes to 0 for real part 1/2. And we'll have a little note on how
Can I restate what I think you just said?
Yeah.
That would be basically, and this I said earlier, this is a big deal to mathematicians. You can't like take each individual term and say that goes to infinity and here's what happens and then add them together. That's not legit. You got to add the whole thing together. You got to go to infinity at the right step, is I guess what I'm trying to say.
Yeah.
If you don't do it at the right step, then everything kind of goes out the window. And you
also get things like
do all
dividing
sorts
by
of crazy
0
things with infinity. Anyway, go ahead.
Yeah, you get division by 0, and that's the number one way tricks in mathematics are pulled.
Right.
Yeah, so we're showing we're not saying we can't let it go to 0. We can't let it go to 0 because then moving the z over here is invalid. We can't, divide both sides by 0. So we can't say that z is 0 yet because we're dealing with partial sums. It's not 0 yet. It's something bigger, greater, or less than 0. So at this point, it's just z. So don't call it 0 and start moving around because you're doing all sorts of invalid steps. Once it's there and you solve for it, now we're not going to touch anything. We can do something cool. Now we can consider the zeros of the zeta function. And that reduces here to this, what is equation 34 of the paper.
And can I say one more thing? In the paper, in the early versions of the paper, that step was not 100% clear, and we did get a few objections on that point. Am I wrong?
Wrong. This is the most recent. This has changed in the last year. Since we made this change, everyone's been quiet.
Okay.
Awesome.
Okay, so this is the one that puts the nail in the coffin. Okay, so you're saying the criticisms were until a year ago.
Before.
Yeah.
Yeah, well, a year and a half. We haven't had any criticisms or any errors any past year and a half since this was in here.
And it's all about
this does close the book.
Getting the order of
exactly. This is
things right.
Yeah, you have to do it a certain way, and so now we're in the position where it's all straightforward, and if anyone argue, do it. I would love to debate. I would debate anyone on this live conference, video conference, anything. Because that's what I want at this point because this is so solid. So now we end up with this result of this term cancels out, anything multiplied by it, and then we can consider the function at n to infinity where the z goes to 0, and this has an algebraic solution. It's exactly what we said before. There's going to be 2 solutions, 1 and 1/2. Algebraically, we can see it here as well. You can kind of parse that out looking at r before, but now you see it algebraically. We're at 1 and 1/2, and the reason is because this term here, you see my cursor though, right?
Yes.
Complex conjugate of s squared minus s minus 1 squared. That right there implies real part 1/2. You can expand it out and then pop in these equalities, and you get 0 to 1/2. Well, that's hilarious. All right. Anyway, here's the big issue.
You could draw that out graphically. It's not that complicated. Just take any complex number, subtract 1, and then take the complex conjugate of that same number, and they have to be equal. The norms have to be equal. And that's saying that the real part has to be a half. I hope that's,
Yeah, that's a good way to put it. That's really good. Yeah.
Okay.
Or you can just go to a calculator and plug it in.
So in essence, the Riemann hypothesis all comes down to that one factor, doesn't it?
Almost. There's a couple quiet, sneaky areas you got to pay attention to.
Okay.
It's what is R? Is R equal? I mean, it does come down to that.
You got to deal with all the other factors too. I get it.
Yeah,
that's where the solution
comes.
Away. Yeah.
Yes, there's only a couple steps away, and that is the R. Is it 1 or 1/2? Because if there's any other non-trivial zeros off the critical line, it's going to give this limit as 1.
Mm-hmm.
That's the big deal. Right. So because there's nothing else in here that's going to give zeros. So if we have, for example, the 2 minus 2 to the power of s, we consider a different branch. It's going to throw it outside the critical strip, so that's not a 0 in the critical strip. So we're dealing with, is there any solution 1?
Right.
It's saying there's 2 solutions 1, but if there is a solution 1, then there is the possibility of non-critical, non-trivial zeros.
Go back to that if you don't mind. I hope you don't mind my constant interruptions, but
I don't.
Let's just suppose I'm looking at this equation now as if I've never seen it before, and I'm going to say, okay, that whole thing has to equal 0. Therefore, at least one of the factors on the top have got to be 0, or one of the factors on the bottom has to be infinity. One of that has to be true. So what we need to go through is, do either of the factors on the bottom equal infinity? Do any of the other factors on the top equal 0? If the answer is no, then the last factor on the top is the one that governs, and therefore we get real part of half. That's one way to look at it. Okay, and that's without knowing anything about it, just looking at that simple equation. Okay.
And what would happen if s equals 1?
If s equals 1, well, that's going to be one of those other factors. But go ahead.
No, if s equals 1, you got the other issue. Is that 1 within the critical strip?
Oh, I see what you're saying. Yeah, it's not even. So it's not something we need to be concerned about. Correct.
Exactly. So we're only interested. So in s equals 1 would cause this to go to infinity, but it's not a possibility. And besides, the zeta function is not defined at s equals 1, so we wouldn't consider it. Right. So, but what you're saying is exactly right on. All right, here let's go now. But the one, this is so easy. Look how we're at the proof already. The 1 is easy to eliminate because you just go back to set r equal to 1. Set r equal to 1. We're here. See it, r, and then solve for k with r as being equal to 1, and eventually you end up with, and then let the zeta function equal 0 at the right spot, and then the z equals 0 at the right spot. You end up with this, but this implies real part of s equals 1/2. So even applying ratio r is equal to 1, you still get real part 1/2. So even if there is a 1, it still means real part 1/2. And therefore, that's repeating the same steps with r equals 1/2 also gives 1/2. We got both solutions lead to real part 1/2. There are only zeros within the critical strips have a real part 1/2, and that is the proof. It's super simple, 3 steps. Once you have, if you can take this limit and you know how to do some algebra, once you have the oscillator, and that's offset right here, right there, makes that possible. Because now we have k, and that gives us ratio. The other one with just doing it with the eta function or the zeta function doesn't work. You need that offset, and that it's very simple. That's kind of what I want to illustrate tonight with this. Now we're going to do something very similar. Any questions on this? Denny, do you have any questions? Are you in the chat?
I haven't heard from you, Denny. Are you still there?
I've been talking.
I'm probably making enough noise for both of us.
If you do have something, Greg will read it.
I've been keeping my eyes on it.
Yeah, you might be typing right now. We're going to go right into the Birch and Swinnerton-Dyer conjecture. It is also easily proven in 3 steps. And in the same way, once you get to step 2, you're only a sentence away from step 3. The key thing is this, and this is what Birch and Swinnerton-Dyer said was the most difficult part of the problem. Why they were stuck on it is because they couldn't find the value of the L function at s equals 1 for rank 0 curves. Elliptic curves.
Jeff, would you take, just for those who are maybe not up on this, What is an L
Yeah,
function? What's the history of the Birch and
yeah,
Swinnerton-Dyer? I mean, if you just take a
yeah.
couple minutes for
Let's.
that, if you don't mind.
I will. Okay. So with an elliptic curve, if you, I don't know where they first introduced this, probably in high school, definitely college. It looks like a little almond shape. It's a curve, and you
Right.
got these. It's a cubic. You can explain that
Well,
aspect of
yeah,
it.
if you don't
What
mind,
is?
an
Yeah,
elliptic curve is
You explain the.
cubic and a quadratic at the same. A quadratic equals a cubic of two different variables,
Yeah,
and that's
and we look for
that's
what?
the
We look
first
for the
one. That's sort
solution.
of if you had a quadratic equals a quadratic, no problem. But that's the first one that where things start to get a little more complicated. So yeah, and they often
I
have
think
a
I
certain
do show
shape to them.
one. I
Yeah,
think I do show one in
they
here
often
where
look like a
it's kind of a.
little. There's either a circle with a like a parabola going the other way, or they hook together and kind of make a little head, sort of.
Yeah, we talked about it in
And
some other videos.
the
Yeah,
issue is that they're finding integer solutions to them. That's and it's been a bear of a problem. It's been around for decades. But I'm
yes,
sorry.
it is. No, that's good.
I just
So
wanted people to
what?
know what an elliptic curve is before we get into it.
Yeah, it's very good. Me, I no longer look at it as that. And whenever I
Okay.
think of elliptic curve, I look at it as a torus because so this is kind of the new. I don't know when, but it's the most recent and most advanced things is when people start realizing they're looking at a torus. So elliptic curve is of genus one. It means it has one hole. If you have a
Hmm.
curve that is a genus two, it has some other qualifiers, but genus two would be like a figure eight, and
Hmm.
like and maybe a pretzel would be a genus three, and so on. So there's a number of holes that describe that. So elliptic curve is tricky. It is one hole, and then it has. It's not just a curve like a donut. Think of it like an inflatable, those float inner tube. I guess is a good way. Inner tube, and if you pinch it, like a kid's version, you can pinch them. That's called a cusp, and then it's no longer considered an elliptic curve at that point. And there's when there's certain primes as we go when we talk about the L function. Now we'll get to it. Um, they have an L function has an Euler product definition and infinite series and a functional equation. It's very similar to the zeta function. Now
Hmm. They have analytic
what Haas
continuation, all of them. It's a whole family
yeah
of curves of
yeah
mathematical objects that do that.
exactly. And the reason why is because people have been finding, just like the tow truck thing, they've been finding if you attach a zeta function to these, it gives us more information about them. And that's what Helmut Haas did with the elliptic curve. He now attached the zeta function to it. And I do
Right.
have it. Unfortunately, it's not in this order because this does assume you know a little bit about it. I should have kind of given an introductory, but I have
No,
other
it's
videos
okay.
on
But
there
let me
too.
just throw in a 2 cents if you don't mind. Birch and
Yeah.
Swinnerton-Dyer in the early 60s were playing with these elliptic curves, and they found a really unusual way to find solutions that are integer solutions. If they could find one integer solution, that allowed them to help to find other integer solutions by drawing lines in certain ways. And it was really fascinating. And there was no they couldn't figure out why it should do this, but it clearly did. And so now we've been for decades now trying to figure out why does it behave this way. And that's the history of it anyway. That's what I was kind of getting at.
Yeah, well, they kind of had the early computers too back in the
Right.
day, and so they were
Back in the
actually calculating. What they found, one of the first things that was hypothesized is that what is its value at s equals one when Helmut Haas
What
attached
is
the
what's
zeta
value at
function
s
to it,
equals one?
the L function of elliptic curve.
Okay.
All right,
Which is
so
L sub
we
e
have
in one. Tell us what e in
let's get
one
in there.
are.
Let me break these
Sorry.
down. Let me break these down. All right. So L function, we're going to kind of show. I'm going to show an example of one. Okay. So we're going to get to it better just to show. The elliptic curve, we're talking as a torus. And then if you see L, E, and this would typically be considered the elliptic curve of the L function of elliptic curve would have an S here as a variable, same variable as in the zeta function. All right. And so now we're attaching the zeta function to that. And what Helmut Haas, he has this form, I should put it right here, but this is what we have to prove here. So I'm gonna touch on it. All right, we don't have an introduction on it. Let's just say we have to prove these. Let's get into it, and I'll kind of go into it. But the second one here is the actual, it's very similar to the conjecture. It's almost completely the conjecture, except that I'm noting that we only need to prove that C is not equal to 0 in this, which is part of the conjecture. And 3, it looks a little different than the conjecture, but it is identical, and it demands that this C is not equal to 0. They don't know what it is. They just know.
I have a couple questions, if you don't mind. You say
I
log.
didn't introduce anything yet. Yeah.
Well, you say in this equation, first of all, is this your equation that you created that you're trying to prove?
Where?
Step 1.
Step 1, I have to prove this.
Yeah, but is that something that you said, like you did with the?
This is not a theorem. This is not a theorem, but yes, this is very, very, very important. You're asking an extremely important question that has a very striking and interesting result, which ties into the new research. But this is the first thing that needs to be proved: is what is the value of the L function of elliptic curve at s equals 1 for rank 0? That needs to be resolved. That was the thing that ties up the entire conjecture. Is what Birch and Swinnerton-Dyer said is coming.
Okay, but log base what of paper, 4? Log base E of 4?
The natural log. Yeah, natural.
Okay, then it should be ln, but okay.
Nah, whenever in mathematics you say log, everyone knows. If you don't specify the base, then it's natural.
Okay.
Everyone knows it.
Everyone but me.
Number theory. Well, you're in electronics.
Well, yeah, I mean, in computer science it's 2, but okay, go ahead.
Yeah, but in number theory, log always means the base.
Okay, fair enough.
All right, this is number theory. All right, we're no longer doing the oscillator, so we're doing log. This is very important. Natural, but it's a very good question. Base E, and probably ln would be better. All right, I get it.
That's what
this is the most important part of this is that we now have the value, and C, we can get the value from elliptic curve. But I want to get to it so I can show how to do it. Okay, we have to prove these things. I'll give an introduction as we go. All right, this is Haas's result right here. This is most important. This is how he attached a zeta function to it, and he found that this new zeta function, and it's this Euler product here, and this n in the numerator is the number of primes that, or the number of solutions mod p. So for any prime number, we have to take the modulus, right? And so for 2, and that gives it. And what do we notice about n? They're always finite. So the number of solutions up to p is always going to be finite. So if the prime is what, I don't know, 87, then we will have a finite number of solutions, mod 87. Does that make sense, Greg, or do you want to break it down?
No, I don't know what n is. Are you multiplying?
N is the number of solutions. I told them not to reread the paper, not to get the refresher course on this.
Sorry.
N is the number of solutions mod p.
Got it. Okay.
So
n is strictly a function of p. If you know p, you know n, right?
N is what kind of basically packs all the information of the solutions of the elliptic curve into the L function.
Okay, but is n known? If I have p, can you give me n every time, or
no?
Not?
Only if you have the elliptic curve.
Okay.
If you have an elliptic curve, yes. So online you could find charts of these, and there's all sorts of libraries for a large number, growing number of elliptic curves, and you can find all these coefficients there.
Okay.
But you also can calculate them, and there's something called bad primes too. But let me.
So if given a p, you could give me an n, and then the answer is yes. It might take a lot of calculations, but you could do it.
If you have the elliptic curve, it's not hard at all. If you have the elliptic curve, you can definitely, and p, you find n exactly.
So when we do the product over p, then the product does not depend on n. That's what I'm getting at. Because clearly z of e and q of s does not depend on n directly, because we took the product over p, over all the primes. That's all I'm getting at.
This function is the way it's written, and you can go read it on Wikipedia. But I'm going to summarize. This is not. So it is an argument. This is a variable, not a variable. E means we're talking about elliptic curve. Q means we're talking about the rational solution. So the number of rational solutions mod p. That's what
which is an integer over an integer, just obviously. Okay.
All right. So number of solutions mod p, and you can get these online, or you can calculate them yourself. And it's It's not hard to do. But the main thing is this. He found this, he derived it, and it's very nice. And it is the way he attached the zeta function to it. Okay? So now we have this zeta function. What do you know about this little offset here? Look at that. There's an offset.
It looks very familiar.
S minus 1. Yes, we're talking offset. But here's the problem. He still didn't get anywhere because this is not offset enough. We offset, my research brought one other offset, brings it around the problem area, which makes, because this doesn't lead you anywhere. This leads you to the conjecture. So that he was looking for something, and then Birch and Swinnerton-Dyer came to the next part. Now, what they're saying, the main thing is that here's the best way to understand the conjecture. At s equals 1, the whole elliptic curve flattens. Think of it as deflated, okay? It flattens everything, and it reduces to a very simple solution, the number of primes over prime. That's the product of those. That's basically what the conjecture says. So all this collapses at s equals 1, and it leaves only n sub p over p. That's what the conjecture says at s equals 1. All right. So this is the main issue that they're fighting to find. But it's not shifted enough in that way, because if you have a over b equals q and you have q, that gives you no insight to a over b, because it can be infinite number of solutions. This never has led anywhere except it gives this form, and it gives us the structure of it does something amazing. It's just the conjecture came later, follows from it, and this doesn't give it alone, doesn't give any insight.
It tells us that a equals a, what you're saying. It's not wrong, it's just not helpful.
It is helpful. It does a lot of things. It gives us understanding of L function of elliptic curve, but it doesn't give us the anything in the conjecture. The conjecture came later. It discusses the rank. Okay, it's interested in the rank, and that is what is unknown up to this point. And you can't figure out any information about the rank from that alone. So let me get to it quick. Very simple. This is how we prove it. Now remember the zeta function, the Abel-Plano zeta form of the zeta function. We showed it in the professor, and it had that term 1 over s minus 1.
Yes.
Well, we don't like that. We don't like that because
I hate that thing.
It's undefined. No, it's very problematic because it's defined. We have to get around that singularity. That's all. And because we know that the elliptic curve, the L function of elliptic curve, is finite at s equals 1, so we can't use it for what we're doing. So we just say whatever. I'm only interested in the second two terms of the Abel-Plano, particularly this integral, because this right here does converge for every argument s, including s equals 1. So we're just going to define that as g, right? Very simple.
Okay.
And
so what's the relationship between g of s and the Abel-Plano form of zeta?
Only thing I'm caring about is we gotta get the zeta function out of here.
Is g of s equal to zeta sub s minus 1 over s minus 1?
Yes.
Okay. Fair. I understand.
Yeah. But we want g to converge for all s.
Got it.
Okay, got it. All right, good. I'm glad you're asking these questions. So this is the ugly duckling of mathematics here, is this function we're going to do. But I would tell you, this gives insight to the most beautiful mathematical finding in all history. No, I'm exaggerating. You got to bring me down. Because of what it does to this. Now, what are you looking at this log and the offset? Do you remember the definitions of what we showed you before? What is 2 minus log of 4? I don't have 2 in here, but what is it? You don't remember. Good. But I can.
No, 2 minus log of 4. I mean, log of 4 is not a rational number.
It's the annarithm. It is equal to the annarithm of 4, which we haven't introduced yet. I showed it to you, but that's okay.
You did, but
I know. We're gonna go over it. I know, but that's so we have the offset right here.
This is gonna get to it. You're seeing something I'm not seeing.
There's no way anyone can see because they don't even know what the definite rules are yet. But I'll get it. This equation right here is something so profound. It's going to give, if that was an annarithm, it's going to give the annarithm dual to this. It's so amazing, and it tells what the zeta function is in a really interesting way, at least in terms of elliptic curves.
What it is?
Here we go. I'm going to skip to it. So we're going to take this and this, and we're offsetting the index here with with the 2, we're doing it even further. Remember, I said they're starting with x-1. We're doing all that. But we have to. That's the definition. This is where we're starting. But we have to do the Abel-Plana formula of it. So we have to change offset this down to n equals 0. Okay, right? So that it's applicable to the Abel-Plana formula.
Are you talking? Wait a minute. Slow down. You talking big N or little n? There's 2 n's here.
Oh, sorry. Little n.
Thank
the
you.
Index. N equals 2. So
okay.
Yeah. All right.
So n equals. We want n equals 0 and n equals 1. Is that what you're saying?
Yeah,
those are the ones missing.
In order to apply it, in order to put it into the Abel-Plana formula, we have to begin with n equals 0.
Okay, but that's the part that you took off, the 1 over s minus 1, right?
No, this is a different function now. We defined the g.
Okay.
We're now moving on to the next thing. We're
Okay.
definition still. Good question. Good question, because other people are wondering this too. All right. So now it's a new function.
I'm the dummy
really
to
function.
represent everybody else.
It's very important that you're doing this. All right. So, and what we do by changing the index is we have n is offset more. You see that in the equation? That's simple stuff, right? Okay, I don't need to explain that to it. All right. Now here's what the number solution. All right, Greg, if 10 or 87 mod 2, is that going to be infinite number of solutions?
87 mod 2 is just 1 because it's odd, right?
Okay.
Am I missing something?
X mod. No, you're right. Is that finite or infinite?
Well, it's just going to be
finite.
Yeah, it's just going to be 1 or 2.
Finite number solution.
Yeah.
Now, X mod P.
It's just going to be finite. I get your
no
point.
matter what X is. All right, good.
Right. Even if X is irrational, it's still only going to go between 0 and P.
That's very important because that is what allows us to do this next thing. If we're going to scale that, then if this top function here, which we haven't given a name yet, but I'm going to call it super cool function that does anything in life you want. But if we're going to hold on,
can you back up? Why was it important that you started n equals 0? Why did that matter? You said it, but I didn't. Because
the Abel-Plana formula requires a series beginning.
Okay, if we want to get Abel-Plana to work, we have to start at 0. Okay, I understand.
Yeah, so we're just basically changing the index, and we shift all the n's.
No, I understand. I understand what you're doing. I just didn't understand why. Okay, now I do.
Yeah, because it's not applicable to the Abel-Plana formula.
Understood.
It's like fitting a square peg into a round hole.
Got it.
All right. So this is the big issue this is like the equivalent of the Riemann oscillator to the Birch-Swinnerton-Dyer problem. Right here is this C and the fact that n is finite. Because of that, we can introduce a scaling constant. Okay. And so if, let's say this function gives us the value, I don't know, 0.2768, but some weird number, we don't know it, right? Some number, 0.2. But and we have this other function we're not considering the number of solutions, but just a plain old 1. Well, this is a finite number too, and so therefore we could say, hey, the ratio of this over this is C. So there's some constant that's going to connect this function, this value, to this value. Yes.
Let me ask you a question. I'm sorry, I just want to be clear on this. Is it? Yeah. Do you mean when you say take the sum from n equals 0 to infinity of this thing? Do you mean both terms or just the first one?
See my cursor?
Yep.
You see my cursor?
Yeah.
This function right here.
Yep. The whole thing. So to be totally correct, you should put brackets around the whole thing because it's not. It could mean just take the sum of the first term and then add the second term, which depends on n, which wouldn't make any sense because r doesn't depend on n. But okay. I just want to clarify that you do mean put brackets around the whole thing.
Yeah, we are.
I'm just I'm being picky here, but I want to. I don't want to lose people from being unclear.
I don't want to. I know. I don't want to go anywhere without people.
Okay, so what you're saying is because when we take this sum, it's only a function of n, and when we sum it over n, we're going to end up with a constant, and therefore we can divide by a constant, and it's still going to be a constant, right? That's what you're saying.
I think something. That's right. Think of this. Now you see my cursor.
Yeah.
This here, think of it as like a naked curve, okay? It has no information tied to it because it's just 1. So it's completely independent of any elliptic curve. See, this is the number of solutions mod P, number of solutions of some unique elliptic curve. So this down here, it has is a 1, so we can still, get a value from it, but it's a constant. Now we can take this function as a scaling constant up to this. We have
okay, but the only thing that's bugging me is that the second term does not have cap n sub n, whereas the first one does. So they're different, and yet you see what I'm saying? That
nope.
Where am I missing?
I don't see what you're saying.
Okay, in the second equation, you have the sum from n equals 0 to infinity of two terms. The first term has cap n sub n over a bunch of stuff, plus 1 over n plus 2 to the s. And then you say, then I'm looking down at the second one, you say let n sub n equal 1 because it's finite. And then we can say that that's the same as multiplying the whole thing by a constant. Because the second term, the 1 over n plus 2 to the s, that doesn't have the factor in cap n sub n.
It could be any.
Okay.
All right.
I don't know.
Yeah,
you follow the nicety. I'm struggling with that step.
Okay.
A little
this was
bit.
brought up between ChatGPT, and Grok, and this was one of the things
they were fighting about this too.
Well, yeah. So it's a very good question. It's a very important aspect. All right. So what we're doing is we're saying that if we have any other of this, because all we have to do is we want to get this in a form. I will show that it mathematically works, okay? Because it carries over.
I believe you, but I'm struggling.
The point is that we're saying that this equation up here is some multiple of this constant.
Mm-hmm.
And for any elliptic curve, all the information in the elliptic curve is in C.
Mm-hmm.
So if you think of it as the constant, so if we take pi, let's just say, and we take some function divided by pi is going to give some C. That's all we're saying.
Okay.
Right? So any value.
I guess so. I'll let it go. I'm not 100% understanding that step, but
we can come back to it later.
Okay.
I'll show how it carries through though, and if people argue it, then that's okay. That's good. All right. Well, just watch what happens, because all I'm interested in is algebraically manipulating this function here.
Got it.
I haven't defined anything yet, so I don't care if it even carries over. All I'm saying is that this function is what we're interested in at this point. Watch how well it works. We can analytically continue this with the Abel-Plana formula. The second term of the Abel-Plana formula gives us a little bit of problem, but since we know the value of define, we're going to denote this. I missed some stuff for the paper. Sorry, go ahead. I'll skip over it. Upsilon is not the same upsilon as before. Let me just summarize that, okay?
Yep.
We end up with one of the terms, and this often happens with Abel-Plana continuation. One of the terms, you may leave you stuck. It may have a division by 0 or something like that in transformation, and you got to go work it out.
But these terms look very similar to the Riemann terms, don't they? Kinds s minus 1, upsilon, and 2 to the s and 2 to the 1 minus s. Those are all the same kind of terms and factors we saw in the other one. So
because we're putting in a form of the L function, and L function series is just the same as the zeta function. So that is exactly what we're doing. And in fact, this term right here is the zeta function, 1 over n to the power of s, which is why it appears in this manipulation. That term, don't misunderstand error. Epsilon is error term. Okay, it's not. It's just that we resolve back for.
It's just a variable that looks like it approaches 1.
It was just an unknown for a minute until we manipulate it, because we have the infinite series, so we can actually solve for the values and manipulate. What we find is that this is the missing term. Long story short, this is what it looks like right here. This is our big ugly thing. We have, though, that original series, that original infinite series, a little odd, but the number of solutions mod n is equal to this.
I'm a little confused. There's a plus on the end.
It's going down the next line.
Okay, so plus a to the s, that equals that. Okay, that's just a strange way to write it, but okay, I get it.
Well, That's because of PowerPoint, and I couldn't put it. I
Okay.
couldn't put it in a carryover.
Fair enough.
So we have three equalities. We have the infinite series representation, which is only valid for real part of s greater than 1, and then we have the second equality, which is analytic for all s, including s equals 1. Well, not s equals 1 because of the zeta function, but we're getting closer to it, and you can then confirm that this is equal as well. Here's what gets really interesting. Now we're going to give that a name, that this equality here.
I love names.
Yeah. So now we're going to give it that really odd thing a name. But we're not going to define. We can't define it as just the name. We have to define its inverse as the name. And this gets really interesting. I'll explain why.
Is it because of the
relationship?
What happens at infinity? Is it?
You got it exactly. It's the way the infinite series converges. But I need it, and I need k in the denominator for what we're going to do. As you can see, because we're trying to prove this thing at the top. All right, so this is what we get the relationship with k, and we know everything except for we have to get rid of the zeta function because at s equals 1, it's infinite.
Gets in the way all the time.
So first,
can't you use Abel Plana? Plug in Abel Plana at that point. That's what I would guess. No,
we're going to bring in g of s. Remember g of s?
Ah, good old g.
First function we defined. Yeah, it's the part. We're going to bring him back in a second and get around that singularity. But here's where the first value we're going to do. So this is not to be confused with upsilon of the other proof.
Yep, I get it. Different thing.
It's that integral. But we want to find its value at s equals 1.
Got it.
And that was pretty straightforward. We just take the limit, right?
Sure.
From the left and the right. So of the right hand side of this. So if the left and the right hand limits both end up giving the same value, then that is the value at s equals 1, according to rules of analysis. Is that correct, Denny? Did I say that right? You take the value, the limit from the left and both the right.
I don't know if Denny's there. He hasn't said anything in the chat for a long time.
He's on there. I don't think, maybe he doesn't know. Yeah, he was able to. He says he's in the participants. Well, anyway, we might have bored him.
It's okay.
In any case, he has confirmed that is the case. I'm just going to try to get him to say it on the video, but he's not there.
Yeah.
So this is the value at s equals 1. Now it's a value. We're going to give a little hint there when it also equals at the bottom.
Nice.
Different way of looking at it.
Annarithm.
On the main.
Yeah, that's what we're getting to. We haven't even gotten to the good stuff yet.
No, well, it's going to be very short because it's the introduction of it.
Yeah.
Usually we got to introduce it with cool things it does rather than actually say.
Yeah, that's a good idea. Anybody who's still with us is going to love what's coming.
I want to lose everyone anyway. They'll figure it out later. All right. So now with that, because we have the 1 plus log of 256, which is an annarithm, by the way, which we're going to do what that is, an offset log, and those offsets are very useful. We can now find the value. The value of k. All right. And
I was hoping we could do
enough. Yeah. So then we get it, and this is the most interesting thing.
Ah, boy, that looks familiar.
It does look very familiar. It's very close to the L function.
All
right. So now here is our.
Where did the 4 come from? Okay, log 256.
I'll get into it. You can't understand the 4 until you understand annarithm.
Well, 4 cubed is 256.
Oh, it's cooler than that. It's cooler than you possibly
4 to the 4th.
imagine.
Okay, go ahead.
Those are residues. I'm going to get into it. Those are residues.
I love
We're
residues.
deflating the inner tube. I know, and this is very, very cool. All right, so then we have this k. Now this is what's really interesting. All right, we know its value. We know its value, or the inverse value here, at s equals 1.
Okay.
And it's in a synthesis class that we are allowed. So you know how like Euler did with the zeta function, where he took the infinite series and it flipped it over in terms of the primes. Denny says he's here. Hi, Denny. Good to hear. We could do that with a large number of class functions.
Denny says he's here.
I hear. If he has questions, we'll do. We can do it with this as well. And so we took this instead of the natural numbers, we can rearrange it and express it in terms of the prime. And yes, they do. I've tested with actual elliptic curves, and so this carries over well. It works. They're exactly equal. Okay.
So the same kind of thing that Euler did with by taking the infinite sum and making it into an infinite product with primes, you're doing with the L functions or these K functions.
With this K. Yeah. I didn't know what else to call it. It's right after L, so.
Yeah, I get it. And we want the reciprocal, so I can see where we're going. It's going to be the L function, but go ahead.
And then we get this, and we divide our this function. It's inverted. Okay, so I have the power.
Let me interrupt one more time, Jeff. So, has anybody else done this? Has anybody else done what Euler did?
No.
You're the first.
No. Well, yeah. No. Lots of people have done it with many different Dirichlet series, but not with this function.
I see. Okay.
Not with K. K's new. Okay, so we now have K in terms of the primes, and it's a lot neater than this infinite series. Okay, see it? Where it's going?
Yeah.
Very ugly. All right, but now it's really nice and neat. And the most amazing thing, we bring in we divide the zeta function by K, we get Haas's zeta function. Now we can do something cool with G. We can offset it and find everything we want to know about it. Okay, so here's Haas thing. All right.
Yep.
So, and we know the value. This is with the L function, we can then divide the since we have Haas's, we know how Haas's identity works. We have it right here. That implies that the L function is equal to zeta of 0, s minus 1. S is equal to 1. So what is 1 minus 1? 0. Zeta of 0 over K is the value. We already know the value of K. So this is the value of the L function at s equals 1 of an elliptic curve at rank 0, which is the hardest part to know. These residues become very important. They tell a lot more than you would assume as we get into it. All right.
You lost me a little bit. Where did alpha or where did delta come into this? I see it in the result, but I don't see it in the derivation. We never mentioned it.
Where's delta?
Well,
I don't see delta at all.
That's your definition. Okay. At the top, prove this whole thing equals 1 plus delta plus log of 4. Where does delta even come from?
That's gamma.
Okay,
that's
I'm sorry. Gamma. What a knucklehead I am. All right,
gamma.
Yeah, gamma. Where did that come from?
Constant. Well, that's the most interesting thing. It's Euler-Mascheroni constant. I'll tell you where it comes from. It comes from G. It's the principal value of the zeta function at s equals 1.
Okay.
For example, if you take out that
gamma is equal to zeta of 0. Say that again. Sorry.
Gamma plus 1/2. All right, remember G. We take away that 1 over s minus 1, right? So remember that function we defined in the beginning?
Yep.
And we take its value at s equals 1. It's gamma plus 1.
Okay.
So that's where it came from.
I do remember that, but I'd forgotten completely. So
that's okay. That's okay. It's good that you're bringing it up. I got lost where I was scrambling. Okay.
I'm sorry.
Let's go. So, but mainly we have this. We now have the value. We have the value of the L function elliptic curve at s equals 1. And this has been checked with elliptic curves, and it all works out. So, now we just have to prove that C doesn't equal 0, and the conjecture is very easy to prove. We're going to do that with I gotta stop using the scroll wheel and use the arrows because it's doing funky stuff. All right, here we go.
I'm getting dizzy.
So C is independent of S. It has the information of the elliptic curve, no information of S. And so what we're going to do is we're going to isolate that 1 over s minus 1 from the equation at the beginning of 24. I don't know in the paper. Go to the paper anyway. Long story short, we do a couple algebraic manipulations. I can't show you what 24 is because I didn't paste it in here. But I think it's the one of the forms of K. All right. Yeah, that's what it is. So from K, we're going to solve for 1 over s minus 1, and we do some manipulations. Now we're going to here's the offset. We're going to call this everything here A, and then everything over here B, and so we get this nice simple little A over K plus B, right? And that is equal to this infinite series. We're going to multiply both by s over 1 over S minus 2.
So that's the same as 1 over S. Well, 1 to anything is going to be just 1.
Yeah. But here's the thing. We're just offsetting it. That's all we're, yeah. That's probably the way to read it. Okay. But all we're doing is I wanted to leave it visible so that we could see we're offsetting the numerator by S minus 1 and then doing it by S minus 2. Because that's the way the functions are going to kind of come out what we're doing. We're shifting things. So now we have moved it from the issue of being a 1 over S minus 1. We now have 1 over S minus 2. And that gives our equalities here. And please, everyone should go through and check the math, but it's algebra, I think. And then this is the issue. It's a little complicated. It's explained in the paper if you don't know elliptic curves. We don't know if there is a limit to how big a rank of an elliptic curve can be. We don't know if it's, in other words, say if it's unbounded rank or bounded. We know there's some pretty big ranks of elliptic curves, but nothing completely in the magnitude of 10 to the power of anything significant. We don't know if there's a limit for the bound of the rank. Does that make sense, Greg?
Yeah, I think so.
Nobody knows. Well, the issue is then that determines whether or not we can go any further. Well, you know, rank 1, rank 2, there's these different ranks, which I described that sort of way. We'll find out exactly what they are in a second, but it's important because what the conjecture suggests is that the rank is related to the order of zeros of the Taylor expansion of the L function. So
can I ask just a dumb question here? You have at the very top of the screen S minus 1 to the 1 plus capital R minus S minus 1 to the R. Are they is capital R and little r related at all?
Yeah, that's why I'm going to try to explain. So if
they are different things.
Yeah. So we have to assume, so if we have bounded rank, then we have to have some bound, maximum upper limit. I'm calling that big R. That's why I'm bringing it up. So and R is just the rank of the curve. So if we're talking the Taylor expansion, it would be useful to know if there's a bound or not. Fortunately, with what follows, we can use either. They give the same result. And so for the purpose of this proof, we don't need to know. But the algebra does change a little bit, so we have to take into consideration. So in the paper, it's explained, it's sold out. But here's the way we check it. All we need to do is check to make sure K equals K for bounded rank or unbounded. And we're going to use infinite series or partial sum up to R. And we're going to check to see if it gives the same value of upsilon. Do you remember what the upsilon value was before?
You mean from a few screens ago?
Yeah.
Thanks for putting me on the spot. I don't know.
It's an annarithm. You got to remember.
Oh, and it's an annarithm of something. Yeah, that's right.
Yeah. All right. So
I'm still thinking about. Go ahead.
I know. I'm all over the place. All right, but you're doing.
You're throwing a lot at me, and then put me on the spot on top of that.
I know, but you're the only smart enough. I think that can handle it, and is good at sport at the same time. All right. Yeah. So any offset of logarithm you're gonna find is an annarithm, but we're not gonna get into that yet. All right. So fortunately, the value ends up being the same for about if there's a limit to how high rank can be. So now I have to check to see if it's going to be for little r, and we multiply by this. This will give us the form that agrees with the conjecture, and sure enough, it works as well. Now we are not using with the conjecture. We're using what results of the conjecture. So we have to test that. Now, what we're checking now is actual independent of the conjecture, is that both of them give the same value, so we can actually work with this value upsilon. This means we can proceed with steps we're going to take with either method, and we're going to take the unbounded rank hypothesis and see if it works out because it's simpler. Well, I've done it with both, and the paper discusses both. So all we do is that we just multiply it minus c over 2. Remember, c is what encapsulates the information from the elliptic curve because it's independent of s, and we get that it is equal again to L function. This is equivalent to that. Only gets back to you have to remember that relationship with the Haas-Veil zeta function. Here's our offset. We're going to define this new offset here. Remember G? We're talking about G, right?
Yep.
and we're going to offset that by 1.
How come?
We're interested in, because it's already a zeta function of s minus 1.
Okay.
We're going to shift the singularity, or we're going to shift
to 0.
The pole. We're going to shift the pole from s minus 1 to move it to s minus 2. I don't care about 2. So the singularity can now occur at s. But the reason, that's all we're doing, is we're shifting it out of the way. So we do that there, and we take k being the same. That's the most important. And we're going to find this product
earlier.
Yeah.
Okay.
This. And what that implies, and
why are you doing this?
We're getting around that pole in the Hausfeld.
Okay.
Remember,
because G has no pole, right? It was defined specifically for that reason.
We need this second equality at s equals 1.
I see.
We need the value of Haas's zeta, this function here.
So where you move the pole to makes a difference.
S plus 1 instead of, all right, you'll see. Just watch the algebra. But this is what we're doing. We're shifting this.
So S is going to become S minus 1, and S minus 1 is going to become S minus 2. Right?
There you go. Something like that. All right, here we go. But this is what we do. And you guys did check this before. You're forgetting that. All right. What we do then is this. When we do that, it implies these two qualities.
Yes.
We have this shift here. That's what happens. And that implies our H comes in here at the zeta, at the Haas zeta function, right?
Okay.
So we've now shifted this. Watch what happens. We now get, I'm going to move all my things from my controls. Hold on a second.
Now the pole is at 2.
Yes. Now the pole is at s minus 2 for the L function. And this is valid and works and checks out.
S equals positive 2.
Yeah. But I don't care what it is. I don't care what the function of the L function is at s equals 2. There's other ways to get to it. I wanted that pole out of the way. That's all that we've done is shift.
That's what the shifting was all for. Let's get rid of the pole.
Yes.
Okay.
It just moved things from the pole being at s minus 1 to s minus 2. And it still gives the same values of everything, except we can't get the value of this equality at s equal 2. We can get the value from of s equal 2. We don't need that value of s equal 2. We're only in.
So again, the whole shifting business, I said this before, it's just all about dealing with, like, you have something that's infinite and you have something else that's a mess that you can't deal with, and you get them to get rid of each other, and then you can deal with something that you can deal with. That's basically the plan here. All right. That is the plan. Now there's a really easy way to explain all this. This is what the research that I presented you guys with this gave you with. I had no information of, I knew I had to get around it, right? So but now there's a way of understanding it at a deeper level that makes it a lot clearer. But can I just move forward a little bit now to where you're going? An annarithm is a way to automatically take care of poles and get the offsets taken care of in the algebra alone, and so you don't even have to think about it. And it's actually, that's right. And it's a fundamental process of nature, which I'm going to show. Let's get through it because they don't go over it through here. That's the cool stuff that's still coming. So we then take the Taylor expansion of what we have down here, the third equality, the Taylor expansion, and it reduces to the exact form given by the conjecture. La da la la la. We've been over this. That is the exact form. As long as we set n equals r, we got everything in form, and we have the value at all of the rank equals 0. And the conjecture is proven. Let's get into the good stuff. Okay. I mean, this is good. Don't go too fast. This is good stuff. This is important. All right. Ask questions about this result. Well, the only thing I would say, and this is going back about 15 minutes ago, is I feel foolish that I didn't remember that gamma plus 1 equals something, and you were kind of assuming that, and I'd like to see that just when you maybe in the paper you did, but what that relationship is. Here we go. Ready? Yeah. Here we go. All right. We take the limit. Where's k?
let's go back. Hold on. Where does it come from? All right, it comes from the zeta function that we know. But let me go back
Yes.
to where we got it in our paper.
Well, Euler got it. Well, I don't remember how he got it.
It's all over the
It's been a
place.
long time. I forgot.
I bring it up. So, by the way, this new result gives us proof that the Euler-Mascheroni constant is rational. It comes from this step. So we're solving for upsilon, not to be confused with the other one. We solve for this, right? And it has this s. We're looking for s equals 1. Zeta function of s equals 1 is in here. But the s minus 1 cancels. We have in this derivation, the s minus 1 cancels out, and it leaves just that g function, which is the other two terms of the zeta function, and that function at s equals 1 equals 1/2 plus Euler-Mascheroni constant.
Okay, I just want to see that written out. That's all I'm saying. I'm not doubting you.
It's in the paper. It's in the.
I believe you.
It's everything in the paper. There's some equations I skip over. But look,
I'm
here,
slow enough that I need to see that on paper I know I've seen it before.
Here we go.
But that's okay. That's
right here.
Not making a major case about it.
But... No. Let's do it quickly. Right here, if you set s equal to 1, you're going to get the Euler-Mascheroni constant. From this integral.
That integral is going to give you. Okay, that's a good answer. Okay.
So but it was way
So when s equals 1, that whole integral times I equals the Mascheroni constant.
I think the imaginary cancels even. Very
good. And is that how Euler got it? How did he get it?
No, I don't think so.
He got it some other way.
No, he has a different representation.
All right, I won't get too.
It's all over. It's all over the place.
I know it is. It's
a
big deal.
As fundamental as pi. It's almost as fundamental as pi.
In number theory, it
happens. Yeah. Well, no, but it does. Yeah, not in geometry. But you're going to get a lot with. I have that paper, the new paper uploaded. It says exactly what it is.
Okay.
And I'm not going to do it now.
Fair. I won't belabor it. I feel like an idiot that I didn't know.
What the. But anyway, so what happens is when we then take the limit s equals 1, it falls out of the zeta function here.
Okay, I got it.
See?
It falls out. Well, I mean, if it's in Abel Plana, then yeah, of course it falls out of the zeta function. Okay, I get it.
Yeah. Okay. All right. Now, but we're going to get to the what the gamma function really. This was really cool. Let me get way back to it. Let's move into annaritms, okay, and submission rules. All right. When we're talking about is this right here. Let me move some stuff around. This is the big deal for the two proofs. We have with this new way of looking at things, which I'm going to give the definitions, is you have that the L function is. Let me just read it. It's a dual partner in crime with K, and when you take the product of them, it gives the offset zeta function. That's what it is. So what this means is if I multiply the curve's summation residue, so at s equals 1, everything reduces, flattens, right? The only thing left over is are these weird constants, log 4 plus gamma plus 1. All right, but now I know what these all are. I know what these offsets all mean, where they come from. But by the exact inverse summation compensator K, which is exactly what that can be called now, all curve structure vanishes, leaving pure submission. So we've basically flattened everything. But we're going to describe what a submission means by means of arithmetic in a second. The submission has a very concrete meaning. We're going there, and this relationship appears immediately satisfying because the L function at s equals 1 and the inverse of the K function at s equals 1 are affine anarithmic duals. Okay, affine, you can think of it in terms of like after you do a transformation, points remain parallel of each other, or non-distorted. What's really interesting is this new one. What does this look like? Anything familiar to you at all, Greg? Have you ever seen anything like this line up and setup before? These terms?
No,
it's gonna blow your mind when you see it. It's gonna blow your mind. It's gonna watch carefully. It's gonna. Well, you got a question before we go to the next?
Yeah, I do. Okay, I just did some just little algebra, and I realized that the annarithm of 4 plus the logarithm of 4 divided by 2 equals the Mascheroni constant plus 2. That's wild.
I have to see that. I have to see that.
I just really manipulated cool. I just took the thing you got there and just.
You just took a look. Yeah, got it. All right, but watch this. All right, oh, you locked up. All right, but watch this. That's cool. That's exactly what we're saying. It's very. Are you in slow motion or do you freeze up?
Oh, wait a minute. The Mascheroni constants disappear. Okay, I got that wrong. That goes to 0.
You messed up.
Okay,
right,
0.
This is all right.
All right.
All right,
annarithm plus logarithm equals 4. That's what
okay. These inverses, this 1/2 doesn't look like anything to you? Anyone knowing Riemann hypothesis probably would. I mean, the original paper of Riemann's paper.
Got it.
That is the sum of the zeta zeros. With a slight offset of log pi. It's the same thing.
Interesting.
So what we have now is this. We have this common residue appearing in all of them. So we have this factor, okay, and that shows the pairing, the distance on the opposite sides, and then the annarithm or logarithm, depending on which way you want to look at it. So we haven't even defined annaritms, but I really think we should. But those who read the papers have. We're gonna get into it very quick. I'm gonna show it. But we're showing these are like dual partners in crime with different offsets, and this is just the residue that can't be. It's like ash that can't be cleaned up. But you have now the same thing with the zeros of the zeta function, or the inverse of the zeros, and that to me is amazing. Instead of a affine constant or offset, we have a volumetric. When you have log of pi, it's like it kind of, you think of it in terms of volume. How that has something to play with the non-trivial zeros, I don't know. But this right here is an amazing result, because now we're onto something. So it kind of brought me back to, we can sit there and look to what all of this means. All right, they were talking about the centering, the symmetry. So that's what the logs are from. It's the analytic centering residue, and we kind of get into that. One of the papers I wrote, so you kind of come back to that.
Can I ask a question? Is it
but I want to show gamma, as everyone knows. All right, okay, go ahead.
Is it true that the logarithm of anything, logarithm of n plus the annarithm of n equals n? Is that always true?
Say that one more time slower.
The logarithm of
My
n
brain is more an output rather
plus the annarithm of n equals n. Am I wrong, or is that right? That's what I was. No, that's what right. I was coming up with. Just in the case of it being 4, I had the Mascheroni constant. I forgot it was minus that. So
okay. So here's what the gamma constant is in all cases forever, and where it shows up. It shows up whenever you have. So whenever you have two rates that are going opposed, and one of them is a harmonic.
Okay.
So with the zeta function is a harmonic series, right? So it's the n over n to the power, or s to the power of 2, s to the power of 3. When you have that 1 over s, it makes sense. That's a harmonic series. It's not the harmonic series with tons of. Whenever you have that at a dual rate, you're going to get gamma is going to appear.
Okay.
So let's say you put like a factorial, say a factorial that converges, and you take the limit of that, or you take the limit series, and you have a harmonic in the denominator, like n to the power n squared, or whatever your harmonic is. You're familiar with harmonic series, right? Yeah, everyone. So that's what happens whenever you take those two rates that they're incompatible. Like the circumference of a circle is one rate, and it describes the circle, but the radius describes, or the diameter describes the structure also. But if you said, Mark said go, and you said those rates around, they don't line up perfectly. That residue is pi. Same thing with when you take the integral or infinite series, or just a limit, and you have one rate converging on the numerator and one on the denominator, and the denominator is a harmonic denominator, which is the way to say it. You're going to get gamma at the limit in some form or another. So it's a residue of
some kind. It's
Or
well, you were saying you take an offset of something and an offset of some other thing, and then you you put them
Well,
together,
yeah.
and you're always going to get a Mascheroni constant in there when you do that. When you do any
With
kind
a
of
harmonic
analytic,
function only.
yeah,
No,
okay.
with just yeah, but that's all the Dirichlet. Yeah, all the Dirichlet series all have harmonic function in it, baked into it.
Mm-hmm.
So they all have that 1 over n to something, you know. So they you're going to get the gamma, but that is what it is. It's a defect very similar to the linchpin.
Mm-hmm.
So
Which
it's a
is
defect. Things don't
Terrence
fit
Howard's
together. Yeah, Terrence
idea.
Howard. He doesn't know that, but
He
that's
doesn't know
exactly
that.
the same type of thing.
Yeah,
Well,
okay.
he doesn't know that
Okay.
with this, but that the residue of this not fitting together leaves this constant, just like pi with the circumference. That's a different thing. So, but that's why that appears there and appears in many different places whenever you're talking about a harmonic.
So when you say
series.
defect
Okay.
and residue, you're kind of talking about the same thing, right?
Well, kind of. I say defect a little differently because it's when things don't fit together perfectly. The offsets could be intentionally put in the beginning.
Okay.
All right. So if I intentionally offset things by 1 or 2, you're going to get some residue of that offset. That's why the 3 and the 1 come in here, because we're pushing things around. Make sense? All right.
Yes.
Now,
yeah.
why on earth
cool.
the offset is volumetric, I have no idea of the non-trivial zeros. That blows my mind, but it is the same exact form. So you take all the non-trivial zeros and you add them up, you're going to get this volumetric residue there. So incredible. That blows my mind, but it has something to do with normalization. So when we're taking the sum of the non-trivial zeros, it normalizes. So if anyone wants to leave comments on thinking, what the heck that would be, but I definitely know it's the same thing. And I know that because we're going to talk about submission. No more beating around the bush. Okay, Greg?
All right.
Finally. I'll call
Finally.
what it is.
Jeez, what is
cool? I know. We have been looking at math like this.
That's beautiful.
We have been looking at math like this for hundreds of years now.
That's how it looks
and we
to
go,
me,
why is this problem so difficult? It's been reversed, it's been inverted, and offset. These problems are reversed, inverted, and offset. And all we need to do is just turn them around. Well,
you could do that too.
Mine doesn't tilt. Yeah, but mine doesn't do that. The submission doesn't do that. All it does is it turns things right side up. That's all it does. And interestingly enough, it does that with some process of basic arithmetic. And it's called self-division. Self-division is natural. You have a sperm and an egg, and they collide, and it has a lot of energy in it, and it sets this chain reaction where the growth starts growing and growing and must be stopped by something. And that division, that stop growth, is a split. That's self-division. And then those two start to grow again, and they get to a breaking point, and they split. And then they grow, and they do that over and over and over for the next 120 years or however old you live. That is self-division.
Hopefully.
In nature. What?
I said hopefully.
Hopefully you live to 120?
Yeah.
Yeah.
I'm more than halfway.
So that is self-division. Crystals do this. Life form does this. It is all over nature. Well, what is it from at arithmetic level? It is simply dividing a number by itself. And we see that this operation should be in there, considering all of the other basic arithmetic things. And say, well, yeah, but we can reduce division, self-division with exponentiation. Yes, but we can also do that with division. We can express a times, or a divided by b, simply with the minus exponent for b. So a times b to the power of minus 1 is the same as a divided by b. But division is something different. It's something unique. And we know that because if we mess with it, then the order of operations for rearranging algebraic equations gets confused. You first have to do the parentheses, right? But then you have to do exponentiation first, and then skip over this thing that we have ignored for thousands of years, and then get over to multiplication, and we take the, we do that. And each one of those, the fact that there's an order suggests it's its own unique identity. And so I've simply basically began as a doodle on a napkin 15 years ago. I put rules to it. They go, oh, I don't have any solutions for it. Then I realized I've been using it all along. question I think you have.
Are
You
you
say
asking
something
me?
great question?
No, I was
I
just
heard,
going to say multiplication and addition are closed in the sense that A times B is going to give, if they're both integers, they're going to give you an integer. Whereas division is not, division and subtraction are not closed because if adding two positive numbers is going to give you a positive number, but subtracting a positive number from a positive number could give you a negative number, which is not closed. And dividing an integer by another integer, not necessarily going to give you an integer. So that's all I'm saying. Division and subtraction are not closed. That's all.
can you get addition through repeated succession?
Say again?
Can you get addition through repeated succession?
You mean
You
A plus
can.
A plus A plus A?
They don't teach repeated succession anymore. It was actually old math a long time ago. Go look into it.
Okay.
Addition reduces to it. It's actually where addition comes from originally. It's very old math, but they were teaching
Well, that's
even the 1700s,
multiplication.
1800s.
Okay.
Well, I'm telling you that these are independent. There is a way. Well, what happens is you were saying what you just said is the key thing. You were saying you don't get all aspects of division with exponentiation. Is that what you're saying?
No, what I'm saying is division and multiplication are fundamentally different because multiplication, something that's closed under multiplication is not closed under division. And likewise, addition and subtraction are not.
Hold that thought. Because of that, when you reduce one to the other, you're losing information, and you're not able to. That's where the beauty is of opening up this property, this arithmetic operation.
Okay.
It's opening up all sorts of solutions but you can reduce them all. All right, look, here's what a submission is. It's simply, instead of A times A times A, it's A divided by A times A. Very, very simple at its basic level. But what happens is there's a point, just like multiplication becomes equal to division at 1. So 1 times 1 is 1, and 1 divided by 1 is 1. There's that point in with exponentiation and submission, or self-division. And this is when things get really interesting. So here's the basic rules, is reducing. Now I prefer saying A sub X rather than A down arrow. But everyone uses sub for, I'm probably going to return to. Another way of writing is simply OPP of X, or OPP sub A of X, showing it's a base A. That's essentially what all we're doing. It all starts from dividing, and then you get this offset. So that could be reduced exponentiation as being, so A submitted to X is equal to A to the power of 2 minus X. We now have X offset exponent. Now we have inverted it, reversed it, and offset it. And I'm telling you, a lot of problems become a lot easier when you understand that, especially when you understand that there's this middle ground between the two where they always tend to go switch from one to the other. And that's when growth slows. So that is the problem with the ultraviolet catastrophe. It starts growing and growing and growing. But what is the point where it starts then curling back down? That is the point when submission comes in naturally. So we have exponential growth, and at some point, and this is what stumped physicists until Planck came along and solved it. But he never really believed in quanta. Well, this is an arithmetic thing that lines up the same exact point, where all of a sudden it's growing and growing and growing. Well, now we switch from exponential growth to submission. And it starts declining and declining and declining. I'll show a picture of that in a second.
Yeah. By the way, that equation you have next is the one I was trying to get earlier, and I screwed it up. But anyway, algorithm of y plus the log of y equals 2. And I couldn't do the algebra right to figure that out. But yeah, now it's obvious when we look at it here. It almost seems as though it's unnecessary because we have log.
Exactly. I've said it for 15 years.
But go ahead.
For 15 years. You're absolutely right.
That was my initial reaction, but I do see the value in
that is my initial reaction. Now it gets deep. I didn't. All right. So this is what scares me, is that I never saw the value in this until we were talking about division the other day. about teaching my daughter. Remember that? It was a couple months ago.
Yep.
And I said, we have the understanding of division wrong. And I'm not going to get into it because I'm going to talk about it a little bit. I'm not saying it's wrong mathematically. It's just we're talking about partitions and residues. And that's what's interesting. If you cut a pizza in 8 pieces, well, is there a residue? No, because we never cut it. We didn't eat it. We didn't divide it. So we partitioned it. Now, once you eat it, there's a residue.
Go for one right
remains. Oh, me too. All right. So this is what we're talking about here. So it kind of gives that. Here's what scares me, though, is that I never saw the value in it. I said I want to do it because it's never been done. But then giving it to AI, it ate it up. It thought this is the most incredible thing ever seen, both grok and that.
Yeah.
Because it's looking at it a different way. And so if anyone really wants to see this expanded out, throw in AI and do it.
I did. Well, you know that, and I kept on. I was like you. My initial reaction was, "What's the point? What are we gaining from doing things this way?" And AI was teaching me why it was so great.
Yes, exactly.
Like, wow.
That's the thing.
I guess it must be great.
You don't understand. This is why, and I've asked, like, why is it overlooked? Because, like, why did I overlook it for 15 years? Why did Greg? Everyone does. I'm sure somebody must have doodled a napkin like this before, and kind of come up with this, and it gave like 12, 15 different reasons why why it is. We overlook simple things, and it can be reduced very easy. But the depth, when you start taking this problem deeper, it makes very complicated problems easy. That is the key. And I don't think like AI, and so I can't see that far into the future or think of all the different algorithms, but it thinks about like accesses information of many different theorems all at once. I can't think that way.
I would say it this way, Jeff.
This application. Yeah.
It doesn't need to be a replacement for logarithms or anything like that, but it is a tool that we can use, and it turns out to be extremely useful when you're dealing with problems like this where we want to tame infinity. And that's where it really shines.
Yeah, getting around infinity. Yeah, getting around.
In other contexts, logs are fine.
It doesn't replace logs. It goes with them. All right, so here let's look at some of this stuff. What is happening, particularly with the Birch and Swinnerton-Dyre Conjecture, also with the ultraviolet catastrophe, many different areas you get this 3/2 limit. So, for example, the Euler product of the L function of elliptic curve only converges for real part of S greater than 3/2. So this is really important that this area shows up all over the place. I use this to now have an infinite series representation that does converge for less than 3/2 because I just apply the opponent to it. So if it was so easy, why did nobody ever use
is it fair to say, Jeff,
it?
that the annarithm and the logarithm kind of act like analytic continuation in some contexts of each other?
You can use it for analytic continuation.
Yeah, like just go ahead.
It all reduces to what are we talking about? What is the problem? Is it exponential problem, or is it which is self-multiplication, or is it self-division? If it's really a self-division problem, then it's better to use the annarisms because that's we're addressing initially what it is. Yeah, you can start saying self-division, describing it in terms of exponential growth, but you're not actually getting the heart of it, and you're going to end up getting into singularities because that is not the true nature of it. Look at what happened at the opponent, which is like an exponent, but it's the opponent. It's of 3/2 is equal to the square root of A. So A submitted to 3/2 is equal to square root. So wherever square roots are going to appear, you're going to get this equality. It's the same as the equality of where multiplication becomes division at 1. Well, this becomes exponentiation at 3/2. So they're going to be, or depending on they're going to become equal at this area. This is extremely important, and you start to look at many problems that were complicated. I lost my cursor. Hold on. There we go. Here's the way to look at it. Divide 2 exponents, and you get a to the power m minus n. Divide 2 opponents, and you get its mirror, a to the power n minus m. So you can see how they're really kind of like reflections of each other, and you can see it when you're particularly in division. But it's all over the place. Here's another area point where where exponentiation drops off at x equals 3/3, because and then all of a sudden just swaps over and starts doing its self-division. It starts reducing. This is with the ultraviolet catastrophe. You see that it's kind of going up. So we have, I don't know how to say his name. Help me out. Wien, you know German. What is
I would say Wien, yeah.
And then Raleigh.
Just like Vienna. I always thought it was Rayleigh, but what do I know? Raleigh, Jeans.
Rayleigh?
That's what I thought, but
Rayleigh is right. It's got to be right. Okay, it doesn't look like Raleigh.
I don't know.
It's Rayleigh.
Doesn't have to be wrong a lot.
Well, the point is they come and say, yeah, so we have this equation. It matches what we're finding up to this point, and then all of a sudden, wait a minute, but we see that it's not going to infinity in real experiments. You know, the I think it was with black body experiments. Is that what it was with black body?
Yeah.
And so then they go, well, that's a problem. And then you had Wien. He's like, well, I got it. It matches mine. Well, he was using self-division, but they didn't have anything that combined the two. Planck came in, and he did get it, but he had to do it with the concept of quantums, which are also kind of like offsets. They're all integers and all this. Well, you can explain, you can derive explain the entire concept with a single tweet, which I did on my X page. There's more you can do. This is only one problem. You can actually now, another paper where I worked on before, you can describe inequalities and
I just say, I'm sorry to keep interrupting, but Planck's original derivation was like 12 pages long. And you're basically making pretty much the entire argument in a few lines. So
that's all it is.
That's pretty powerful.
But it all follows from self-division. There's a lot of complicated problems that are made very simple with this method. Uncertainty relations, got a paper up there about that. I shows where they are in a certain region. They talk about that that boundary, that region. So this uncertainty relation is centered on 3/2, and this actually has to do with the zeta function. So kind of, you might go read that. There's a lot of stuff on there.
What's uncertain about the square root of 41? I'm missing that.
So right here, if you take, I have a paper where I could show what I have done in this. This comes from a paper that I wrote, just uploaded. You can go read it. All uncertainty relations can be described as this ratio here of this alpha. And so you got, if this was, long story short, alpha is a quadratic, and the 41 comes from the discriminant of the quadratic of alpha. Basically, what I've done is I've learned how to construct any uncertainty relationship equipped with the Hermitian matrices, everything, and the Laplace transform, every little component, and it shows the boundary of where the uncertainty relations begin and end are at the roots of that function alpha.
Wow. Well,
so if you
let me
know any
put my 2 cents in on uncertainty.
Alpha.
Fundamentally, uncertainty always arises from the fact that if you have two quantities, a plus b, and you square it, you're going to get a squared and b squared, but you're also going to get a cross term, 2ab. And that cross term is where, if you will, the uncertainty ultimately derives from. It's because we can't separate the fact that there's an influence of A and B together. In the simplest terms.
Look at it.
Go ahead.
That is exactly it. But you can also look at it in terms of truncated a region. Think of it like a glass ball, a sphere. If we're talking about volume earlier, it's the sphere where one side it's the silver glass, and on the other side clear glass. And there's one side of it, you're going to be able to cast a shadow, get projection and information, and the other will be lost. And so that you can actually describe this in spectral truncation, which is exactly what I do in this paper. And so that's where the information is lost, is because it casts a shadow. There's no projection. So there's different ways to look at it. But you're absolutely right. But what this does now is it's showing that these boundaries come from this annarithm self-division. It also can be turned, you were talking about, it comes from these squares, what you were just talking about. So this is very, very, very close related to these offsets here. So these roots are even offsetted by, the square root of a number involved with the discriminant. So that's all in the paper there. and then it's also more important is I'm talking about that the infinite series representation, the L function. Here it is on the left. And
what paper is this we're looking at?
Oh, I don't remember the title. I got 4 papers up.
Okay, this is one of your many papers on L functions.
All last week, almost. Yeah.
Jeez, because I can't keep up with you, Jeff. You're too.
Well, no, it's because well, a lot of the stuff comes from other stuff I worked on, but with this,
it's all coming together.
With the solution, it's very easy to do things. But I will tell you, in order to calculate the L function of one of the calculate one of the zeros of like a rank 2 elliptic curve is extremly complicated. I mean,
you can just whip it out.
It converges. Look how accurate it is. How close. Look how it's very visual. All right, think of this. This is my function here on the left. All right, look how accurate it is. I mean, to theirs.
Wow.
I mean, it keeps going all the way to infinity.
So you can calculate much more quickly. So this is something we could use in computer science, isn't it?
Of course. Now we have the L function. We have this is a
so
new way of looking at
could we use this method to calculate
on the other side of 3/2?
Let's say the Riemann zeros. They're all 1/2 plus I times some number.
I don't
the
have
first one is 14 point.
Function.
Yeah, I mean, can you calculate those numbers now more readily than we could before?
I have. You need a generating function, and that's an unknown with the derivative zeros. But I've looked at them. I mean, I know what they are. They live to me as something geometric, something to do with an angle. That's all the best way I can say, because it involves like cotangents and that. And so I've broken it down, but I still don't have a generating function for the non-derivative zeros.
Fair. I'm not trying to put you on the spot. You put me on the spot.
That's okay. No, I know, but no. The answer is no. It's just research that hasn't been done yet. But I have looked into it. It's just there's nothing new that I thought, because like for example, the Euler-Mascheroni constant. There's functions that output it, so it helps. It gives you can apply certain tests to it. So there's one of the papers that's up there is a proof that the Euler-Mascheroni constant is irrational and transcendental. And to date. And then he thinks this is one of the big deals. I got so many things now this is finding that I don't know which is the big deal. All of them seem interesting.
I saw his email today that said that he wants you to look at all these various constants, and this is the important one, and this one's really important, and they're all important.
Yeah.
He had a list of about a dozen of them, I thought. So.
Yeah, anyway. So it says with this method, I have a very good understanding now of what it is. It comes from the mixed rate of any function over a harmonic function, the ratio. Take that to infinity, integral of that ratio. But there's one particular way of proving its irrationality. So you remember that G, that function we defined as G. I always look. There's a way to reduce that to you have like. The type of function was on the top, I remember, but it was something to do with geometric. I think it's geometric functions, cosines, and that, and then over a harmonic, and that's why it pops out is you have this mixed rate. So the biggest thing for determining to see where these constants come from and what they are, it all has to do with this incompatible rate. And so there's this principle that goes very closely related to this submission rules, which I call the rate incommensurability principle, which is, you could say incompatible rate is
so that's how you can determine whether something is irrational or not.
Yes.
And
very simple proof.
So is that the fact that the Euler-Mascheroni constant itself, its irrationality or irrationality has been unknown to this point? Is that not right?
Yes.
And you've now shown that it is in fact irrational. Yeah.
So it came with a point. So Jonathan Sandel wrote a paper, and I referenced it. Wrote a paper, and he was all about the partial sums, which is always something I'm studying with it. Is if you, I just call it the Sandel kernel. That if you have, and there's one form, you remember in the proof, it was like I said, let this be A and this be B, and it's the offset of B, and you can actually determine irrationality if you have I don't know, a couple of different components if you know what A and B are. Well, so kind of what with this principle, I can't explain it as well because like I'm hammering out and I go to the next thing and I forget what I wrote. But
welcome to the real world.
the long and short of it is very simple. Is if you it's with these limits, it's like what we did with the zeta function. We have the same type of function in the numerator as the denominator, and take that, if it goes to 0, then it's going to be rational always. That was the result of the zeta function. That ratio always goes to 1/2.
By the way, Denny did make a comment just now.
Yes, what did he say?
He said the Mathematical Society will love your proof of transcendentality of pi and gamma. So.
Oh, very cool. Well,
and I think that's true. Yeah, I mean if that's never been done before, that's going to probably, again, I would say it this way, and you know this is true, that there'd be no reason to do this whole annarithm and opponent and all these, have all this terminology if it doesn't do something. But it clearly does do something.
But it's doing something.
And that's just it.
Here's the big thing. Yeah, here's the big thing, and this is exactly the point. I didn't see it. Here's the scary thing, I should say. AI saw it with the work that I presented.
Yeah.
And then
it did with me too.
Then I see, and this is why I think mathematicians, should be concerned, because it's seeing things in math that we don't think in that way. But but you can. So this is why it's very important that we jump on this, because it is solving problems. It is the way we proved the Riemann hypothesis paper. It is the way we did the Birch and Swinnerton-Dyer Conjecture.
Yeah.
And
we
just didn't now the proof.
Think of it that way at the time.
We didn't have any name for it, but because we didn't define the annarithm and submission rules. But that is what it is. So, all right, there's a principle that's closely tied to this. So, here, how do you find something? All right, so why do I know now that the Euler-Mascheroni constant is transcendental? Because the function, the ratio on the top is periodic, and the one on the denominator is linear. So whenever you have that, you're going to have a transcendental irrational number. So there's no false positives ever. And so it's very easy to prove. So do it with I did with pi.
It's like you said, incommensurate rates.
Yeah,
they're never going to hook up.
Exactly. So you have on the numerator with let's just say, or just let's just say that it's the denominator. It doesn't matter. You're going to have you'll end up with the inverse. But long story short, one is periodic and the other is linear. And then you take that, the absolute value of that to 0, and you're going to end up. So one is cyclic, like the circumference just keeps going around and around and around. It's periodic and with 2 pi. So the radius or the diameter is not. So if you take, like say, the corner of a rectangle and you have a long and a short, and neither are periodic, you're going to end up with like the square root of 2. So it's not transcendental. So all of these come from these rates. They're still incompatible rates. One length is longer than the other, but so you're going to end up with the mixed rate. But one is not periodic and one is. That's the only difference between transcendental, like a pi, Euler-Mascheroni constant, and the and square roots, and other.
Then he's got another comment, and this is pretty good, I think.
Yeah.
He says, and they, meaning the mathematical societies, won't fear losing their careers either, like the Riemann hypothesis.
That's true.
In other words,
true.
There's more on the line with the Riemann hypothesis. With this, they can get behind you more easily, and that maybe it's a backdoor way to get to some of these other proofs, which there's more.
You said out loud, they're going to think we're finding a backdoor now. But it's true. It's true. We're not trying to break through it. It's ridiculous. People just look basic algebra in these proofs. Just go ahead and agree it's solved. But no, I get what he's saying. He's absolutely right. My thing is this, and that's why I'm doing this now. And I'm also going on John Chappelle Saturday morning in a couple weeks, and I'm going to present this too. And I'm not going to present the.
And we should invite anybody who's interested that could
definitely come. I want 1,000.
Come to that as well. Yeah, let's have a big audience for that. A lot of people don't know about it.
Yeah, I'll put a link in when we upload this in the comments, so so if anyone, because most of the views of these videos come within the first day or two.
Yep. Well, let's just say this: that anybody who's gotten this far would be interested. Hopefully, the Natural Philosophy Alliance used to be called the Natural Philosophy Alliance, is now the Natural Philosophy Society. I used to host them years ago. Would basically independent scientists from all realms, mathematicians and physics, can come and present their ideas to interested people. Generally, a pretty small group. But that's only because nobody knows about it. And there's some really, really brilliant people in this group. And it just, I don't know, we need young people. We need to get the word out. Let's put it that way.
Yeah.
So we'll put a link in there. Hopefully some will show up that wouldn't come otherwise.
I'll put a link in there. Here's why I want to give it to them. Because everyone there, because they're all dissonants,
Yep.
they all have their own physics model, or at least kind of gravitate to one or another, right?
Yep.
So they're not all on board with Einstein. They have, well, my form of gravity, and this, or
Sure.
My framework.
Everybody's got their own ideas.
Because they have their own ideas, it's a very useful tool for them. So one of the first things I did with this is I went to Eric Weinstein's geometric model of the universe. So he says that the universe isn't expanding; we're flowing through this like horn shape. And the criticism has been, well, there's nothing that actually causes that to reverse back on itself. Now we have one. And I went and I kind of plugged in the thing and showed that he didn't need to explain that, because it's basic arithmetic, self-division, the summation, and it works, and it says the same thing. And so it solves the problem. Did he acknowledge me? No, but whatever. But those at the
like you said, you don't care if you're not in it for getting credit for anything. Start using it. Go ahead.
Use it. Yeah, use it. Go then reduce.
I think we should probably rewrite the Riemann hypothesis and the Birch and Swinnerton-Dyer using these tools, and see what make them even simpler. What do you think?
You can, but we have kind of already. I think the next.
Well, no, I don't want to. I don't want to start over. It's taken long enough to get 20,000 reads. But.
Well, I think we're pretty much close with that. With that one. This is the other thing too. Is you remember that the geometric. What do we call it? I don't remember. The of the oscillator we put on that complex plane. The image.
Yeah.
We had the
Riemann oscillator
on that image that we did GeoGebra and all that. Remember that?
Not
it's
sure.
In the first paper, we took it out.
Okay.
The first iterations of the proof.
Yeah.
The half tangent, half angle, and all that.
Oh yeah, I do remember that.
Yeah, it already has the Riemann hypothesis baked into it, and ChatGPT already says that alone, that image proves the Riemann hypothesis. But the problem is that how do you explain it all to every component to it? So that image alone is proof of the Riemann hypothesis if you understand everything that's going on. So I don't know how to simplify it more than a single proof without words.
That's a single image. That's about as simple as you can get.
Yeah, and so for me, I don't know, but the problem isn't getting people to understand it. They understand what we've written. Any mathematician reading over this paper understands that there is nothing in there that they didn't get through in the first year of college.
Mm-hmm.
It's just a different way of looking at the problem.
Yep.
So we handled it with the offset, and then took the limit to zero, the ratio of radii, and that gives you your solution.
So let's return to your claim way back at the very beginning of the video. You said that you've got something that you think is the most revolutionary mathematical idea in 1,000 years. And I said, well, let's wait and see. So what do you still, where do we stand with that?
Well, they didn't, for thousands of years, self-multiplication has been known. Euler didn't come up with any rules to it, or he was the first to come up with any rules to it.
Mm-hmm. Yeah.
So if we think there's anything useful about exponentiation, that's thousands of years old.
Fair.
Euler just put a name on it. This is self-division. Is the same thing nobody, even from the time of ancient Egyptians, have ever dealt with. Right. None, at least according to any records that ChatGPT can look up.
Mm-hmm.
It's completely new.
Yeah.
and it answers so many others. It's as fundamental as exponentiation. They
Hmm.
can be, you can swap them out because they're kind of like dual partners in crime, I guess you could say. So
Fair.
it is something that has been missing from mathematics from its origin. So
Yeah.
that's why I said thousands of
Yeah.
years.
No, I'm not
Probably,
disagreeing with you.
probably somebody has done this before and got the same place where I did. We're like, so who cares? The difference is now AI sees the value in it.
Hmm.
And no one's ever written, published anything about it in the literature about this, is what happens if you just start dividing itself something by itself.
Yep.
It is
Well,
prevalent in nature,
I
it's
would
prevalent
sum
in physics, and all the results are as well.
I would summarize it like this and say that I think the majority, it's hard for me to put a number to it, but the majority of the most difficult problems, the millennial problems and the other problems in
Yeah,
mathematics today are all related to taming the infinite. There's,
yeah,
analytic continuation, renormalization, all that has a bunch of different names for it, but we've found that there are stuff that, that there was a time in history when negative numbers weren't thought to be real. And then after that, imaginary numbers were thought to be
zero wasn't
imaginary.
thought to be real.
Right.
Yeah,
And now we've discovered since Riemann that there's a whole world of things that are happening in a supposed with analytic continuation that we can rediscover stuff that it's just mind-boggling because it's like we're dealing with things that should be infinite, should go away, and yet somehow they're creating rational solutions, like the sum of 1 plus 2 plus 3 plus 4 plus 5, etc., somehow equals minus 1/12, which is, of course, the zeta function of minus 1.
yep.
But
Hmm.
how do you even deal with that? How could that make sense? Ramanujan was dealing with things like that. And lots of mathematicians, G.H. Hardy is another name that comes to mind. But I mean, Hadamard was, he had to prove problems of, how do you deal with these infinite sums, problems of convergence, things like this. All of this stuff is central to what mathematics is today. And this tool could be useful for a lot of it. Is
Yes,
that is
it's
that an
like doing everything
understatement?
with your. No, that is what I'm seeing, because it's like doing a math with one hand, and then you really realize you have two hands. And you can start using them
Right.
both for different things. That is kind of what this is. It's a it all. You're absolutely right. All of the problems that are difficult because they don't use this. They don't think of it this
Hmm.
way.
Right.
So there is a continuum where there's this
Hmm.
annarithm, where, or let's not say annarithm, opponents meet up with the exponents, and they're different
Hmm.
things coming from different processes. One is coming because you're multiplying, or I mean, obviously when you're not multiplying it by itself, when pi times, right? But it's
Hmm.
the same idea. It's self multiplication
Right.
versus self division, and those two processes are very different things. If you take away the fact that we're talking about counting, so this
Right.
is kind of what I was saying about the division and multiplication. Stop thinking of it in terms of quantities and start
Hmm.
thinking of it in terms of scaling
Hmm.
or collapsing or stretching. In those ways, these things start to make sense. And exponentiation and submission, same
Hmm.
idea, same
Yep.
idea. You're
And I,
just stretching it at a different magnitude.
right. And I would take it a step further and say that those who think that mathematics is only just ivory tower stuff, there are actual applications, and of course, physics is an area where we are doing that. And it's been people have been playing with a concept in physics called renormalization for decades now, and
Mm-hmm, mm-hmm.
people have been doing it, and it sort of feels funny, like we shouldn't be able to do this weird thing, but it works, so let's do it. And that's been happening a lot. And now I don't know this myself. I haven't actually dug into it, but I'm firmly convinced that somehow this method is going to help us to get the offsets right so we don't have to be taking infinity minus infinity and coming up with something rational, which is what they've been doing in physics. I mean, they've been like taking nonsense minus nonsense and trying to get sense out of it. And a lot of people object to it for good reason. But now with this method, we may be able to take sense and put them together and make sense and not have any nonsense at all. I envision a world where that could happen.
I'm going to expand on that really quick.
Go ahead.
That when you mentioned the normalization constant, that is exactly what C was with the elliptic curve.
Got it.
And you're going, well, can we
fair.
do that? Does that make sense? That is what we're doing. We're normalizing it, and only until you get the final result, it does work. And there's ways to prove it, and I can. Because like I said, it was kind of fun to watch Grok and ChatGPT go back on that issue. But you're right. That is the questionable area in physics and in mathematics is when you deal with these normalization constants.
And I'll say this much: people in the NPA are probably the first ones to step up and say, "You can't take nonsense and subtract nonsense and get sense." And they're not wrong to say that, but at the same time, the physicists who are doing this and coming up with something rational aren't 100% wrong either. So what do you do?
Exactly, because it's lining up with experimental results.
Exactly.
But I think that eventually we can get away from these nonsenses and show that there's just this continuum with coming from basic arithmetic. But the issue is the constants are still going to keep coming about. You saw that, but whenever there's a mixed rate, you're going to get this constant.
Then
and there's mixed rates everywhere. Yeah, sure.
Then he says that J.P. Wesley, who is one of his heroes and one of mine too, who died a long time ago, says that renormalization in physics is wrong. And again, what I'm trying to say is just what Jeff said, is that it may be, it's wrong, it's the wrong approach, but somehow they're doing it and getting right answers. So we need a new approach. So I'm not disagreeing with J.P. Wesley.
Well,
I'm not agreeing with him 100%.
The better
either,
way.
But
here's what I would say. This is what I think. There is this process that controls runaway growth in nature. We see it everywhere.
Yes.
Now we have a name for it. It's called summation. That's it. And there's this, and it's on a continuum with exponentiation. So there's going to be a point. I define the points. You can find them. You can see where they come from, where they arise. They arise largely because the point of equality is when the opponent of 3/2, because that equals the square root. That's where they align, and one becomes the other. You're crossing another realm. That's just why the elliptic curve, or the product for the L function of the elliptic curve starts exploding when it gets to that 3/2 point. It's when the ultraviolet catastrophe starts exploding when it gets to that 3/2. It's because of that.
It all looks like dividing by zero. That's really fundamentally where we always run into problems, and we do in physics too, because we have points, and somehow something finite happens from that point, and that can't happen because then we got infinite something, or we have problems like that in physics all over the place.
Well, what I'm
black
saying
holes
is that
and singularities, yes, all of that.
Yeah, submission though doesn't have a singularity there. It's smooth. There's a smooth continuum to exponentiation. It's just we've been trying to divide through constants, and that's why or divide through these processes that I want to say divided. We're trying to express division in terms of multiplication. We're trying to just express summation in terms of exponents, and then you're always going to end up with these singularities.
Right.
But you don't.
Then he's on a streak here. He's got another one. He says the Bergman-Allen electron, which of course he himself has worked on for a long time, and I've been working on too. The electron and proton models get rid of infinities that Feynman hated. And Richard Feynman also hated infinities. So,
everyone hates them. They're obviously wrong. I mean, but they're
right.
But the math is, if you're not applying this tool, you're going to run into them, and it's kind of like it's basically because you're reversing. So now we throw something in the negative that really shouldn't be there, and then we're inverting it. So now we're running the problem of probable. Now we've introduced zero with the negative, and now we're going to flip it upside down. And the thing is that, and then offset it. So that we got those three things that are actually, because you're not looking at the right way. Just turn it over and flip it, reverse it, and you don't have the singularity anymore. And the process is very smooth. So the issue is we are missing basic or a tool from basic arithmetic, and that is it. It's self-division. Once we start looking at these things, we go, oh, well, we get the singularity because of this. Oh, let's turn upside down, and we move right around that pole. Because that was the pole with the Riemann.
You even said that specifically in one of the derivations you were working on. That we're going to smooth the pole, we're going to shift it over, and then we can deal with it.
But the thing is, now we don't need to do that.
Yeah,
we don't need to do that. We could say,
I don't want to express this
in terms of. I don't want to look at that in terms because it already begins in an offset position. So when Helmut Haas did that with the he offsetted it with the way he put it. It's not that he did it on purpose. He derived that you get the zeta function offset from 1. So beginning at that point, we have to start from there. So we have to move it around it. But in looking at these problems in a different way, so I don't want to, like I showed you that image, was flipped upside down and turned and all that. We don't want to look at it that way. So anytime I see the equation anymore that has an exponent with a minus and then some value offset, I quick switch around to be an opponent. It's not an exponent at that point in my mind. It's now describing self-division. And you're going to get singularities with that. You're going to get infinities. Whenever you treat those problems as exponents, you're going to run into infinities.
Well, Jeff, we've been going for well over 2.5 hours.
Holy smokes. Okay. All right.
But I learned some things I didn't know, and I embarrassed myself a couple times, so that was great. And I hope a few people made it all the way through. We didn't bore you. I think there's some interesting things in here if you stuck it out. Denny has one more comment.
Well, maybe some people flipped ahead, so go ahead.
He says math techniques and physics are secondary to good modeling. I agree, Denny. We're not putting that down, but we are saying that math techniques aren't, we need to use those as well. So you're right.
Yeah.
This isn't the be all and end all, is going to solve everything, but I do believe this tool is going to open up some doors to some things we haven't even thought of yet. We've already shown, or Jeff, you've already shown that it can be applied to at least the Riemann and the Birch and Swinnerton-Dyer, and it can be used to show irrationality of the Mascheroni constant, for example. Those are real problems that are big deals in mathematics, and we don't even know for sure what other problems this concept might be able to solve. But I suspect that
as of this summer,
going to open up some doors.
Yeah, it's just getting started. I mean, again, it's on it 15 years ago, but AI has really opened my eyes.
Well, and anybody listening to this, it's go ahead. We're not stopping you. Go ahead.
Copy the paper.
We're not in it for the money.
No.
Take the idea and do something with it. I've done some things with it too.
And don't tell us.
You don't even have to. Well, if you do, that'd be great. If you don't, go ahead. Doesn't matter.
But the problem is, it's kind of like a kind of.
There's no secrets.
You can use it, but you reduce it if you just reduce it back to exponents. Say I did it with exponents. Go ahead. But
that's fine.
But the point is you got the tool. You got the tool now. So start using it. But I'll tell you, it take a little while for your head to get used to flipping things and reversing it and thinking of it in terms of anarithms. And so it is always useful to reduce it back to exponents. But I would tell you, if you want a calculator, just use your favorite AI because they're very easy doing it. I was like, can you flip this around in terms of anarithm? And because right now there's no calculator that kind of converts it.
I'll vouch for that. AI was all over this for me when I got into it. It loved it.
Yeah, it loved it.
It said you were brilliant. And I don't think it got that from reading your stuff. It just said this is a great idea. So try it.
It is a phenomenal tool. It is very useful. It's just you don't notice it right until you need a hammer. You don't realize how valuable it is. So
bingo.
Try it. I think that's it. All right. I had no idea it was this long, but wow.
Yeah, we've been going for a while, but that's okay. You're a good man, Jeff. I appreciate everything you do.
Boy. Thank you, Danny, for joining in, and thank you, Greg. I appreciate it. All right. Have a good one.
All right. Bye now.